Hello there, and welcome. Tonight I want to take you somewhere special, somewhere beyond the gentle glow of your bedside lamp, beyond the familiar walls that surround you, beyond even the atmosphere that cradles our small blue world. Tonight, we're going to drift together through the vast cosmic ocean, exploring a possibility that might fundamentally change how we see our place among the stars. It's a question that might initially seem like pure science fiction, something from the realm of late-night movies and speculative novels. But what if I told you that serious scientists, astronomers, and physicists are beginning to wonder about something profound? What if interstellar visitors passing through our solar system aren't the extraordinary, once-in-a-lifetime events we've always imagined them to be? What if, just maybe, they're as routine as ships passing in the night, and we've simply been too focused on our own small harbour to notice the vast maritime traffic flowing all around us? As you settle in, perhaps adjusting your pillow just right, letting the weight of the day slowly dissolve into the softness beneath you, I want you to consider something remarkable. Every single night, while we sleep peacefully in our beds, objects from distant star systems might be passing through our cosmic neighbourhood. Not dramatically, not with fanfare or cosmic fireworks, but quietly, gently, like leaves drifting on an autumn breeze we cannot feel. The universe, you see, is far more dynamic than our everyday experience suggests. While we go about our daily routines, while we sleep and dream, space itself is alive with motion, with objects travelling distances that dwarf our human comprehension, following paths that have been carved out over billions of years. Before we continue on this journey together, and by the way, if you're enjoying this gentle exploration of cosmic mysteries, perhaps you'd like to leave a comment below telling us where you're watching from and what time it is there. It's always fascinating to know that people all around our planet are looking up at the same stars, wondering the same wonderful questions. Maybe you're in New York where the city lights dim the stars but not the imagination. Or perhaps you're in a small town in Australia where the Milky Way stretches across the sky like a river of light. Wherever you are, whatever time zone cradles you tonight, consider subscribing to join us on more of these peaceful journeys through the cosmos. And if this documentary helps you drift off to peaceful sleep while pondering the infinite, a gentle like would help others discover these cosmic lullabies too. But now, let's return to our contemplation of the vast and mysterious space that surrounds us. Think about this for a moment. We live on a small rocky planet, the third world orbiting an average yellow star, located in an unremarkable arm of a spiral galaxy that itself is just one among hundreds of billions of galaxies in the observable universe. Our solar system, as vast as it seems to us, is like a single grain of sand on an infinite beach. And through this cosmic beach, objects are constantly in motion. Comets swing through on long, elliptical journeys that take them far beyond the orbit of Pluto and back again. Asteroids tumble through the darkness between Mars and Jupiter. And occasionally, just occasionally, something arrives from much, much farther away, from another star system entirely. For most of human history, we've imagined ourselves as somehow separate from the rest of the cosmos. We've looked up at the stars as distant, unreachable lights, beautiful but fundamentally disconnected from our earthly existence. But what if that perception is merely a limitation of our perspective, like an ant on a leaf floating down a river, unaware of the vast watershed that feeds the current carrying it along? What if Earth, rather than being an isolated island in the cosmic ocean, is actually located along a kind of interstellar highway, a route that countless objects, and perhaps even crafts, regularly traverse. The idea might seem fantastical at first, but consider how our understanding of the cosmos has evolved over just the past few centuries. There was a time when humanity believed Earth was the center of everything, with the sun, moon, and stars revolving around us in perfect crystalline spheres. We thought the stars were fixed, eternal, unchanging. We believed space between the stars was truly empty, a perfect vacuum containing absolutely nothing. Each of these beliefs, held with absolute certainty by the brightest minds of their time, has been overturned by patient observation and expanding awareness. The stars, we learned, are suns like our own, at distances so vast that their light takes years, centuries, even millennia to reach us. Space, we discovered, isn't empty at all, but filled with gas, dust, magnetic fields, and streams of particles flowing like invisible rivers between the stars. And now, in the early decades of the 21st century, we're beginning to discover something else entirely. We're finding that objects from other star systems do indeed visit our cosmic neighborhood. Not frequently by human standards, not every day or every year, but perhaps far more often than we ever imagined possible. The first confirmed interstellar visitor that we detected, an object named Oumuamua, passed through our solar system in 2017. But here's the remarkable thing. Astronomers calculate that objects like Oumuamua might pass through our solar system regularly, perhaps several times each year. We simply haven't had the technology or the awareness to notice them before. Imagine for a moment that you lived your entire life in a house with no windows, never venturing outside. You might assume that your house exists in isolation, that nothing ever passes by outside. But then, one day, someone installs a small window. Suddenly you see a bird fly past. It's the first bird you've ever seen, and you might think it's an extraordinarily rare event. But as you continue to watch, as you learn to recognize the signs of movement outside your window, you realize that birds have been flying past your house all along. You just couldn't see them before. Perhaps our situation with interstellar visitors is similar. Perhaps we've just recently installed our first small window onto the cosmic highway that runs through our solar system. The implications of this possibility are both profound and oddly comforting. If interstellar visitation is routine, it means the cosmos is far more interconnected than we imagined. It means that the vast distances between stars, while enormous, aren't the impermeable barriers we once thought them to be. It means that material, and perhaps information, flows between star systems as naturally as rivers flow to the sea. We're not isolated. We're part of a vast, dynamic, interconnected system where boundaries are more fluid than fixed. As you lie there, perhaps feeling your breathing beginning to slow, your mind beginning to drift like a boat gently rocking on calm waters, consider what this might mean for our understanding of our place in the universe. We've always thought of Earth as precious because it's unique, because life as we know it exists nowhere else, and Earth is indeed precious, incredibly so. But perhaps its preciousness doesn't come from isolation but from participation. Perhaps Earth is precious precisely because it's part of this vast cosmic dance, receiving visitors from distant stars, possibly even sending its own ambassadors out into the darkness without our knowledge. The night sky, which might appear static and eternal from our limited perspective, is actually a theatre of constant motion and exchange. Right now, as you listen to these words, objects from other star systems might be passing through the outer reaches of our solar system. They might be ancient artifacts, pieces of planets destroyed when their stars died, or fragments of worlds that never quite formed. They might be comets that were ejected from their home systems billions of years ago, carrying within their icy hearts the chemical signatures of alien suns. Or they might be something else entirely, something our current understanding of the cosmos hasn't yet prepared us to recognize or comprehend. The history of astronomy is filled with discoveries that arrived not as dramatic revelations, but as slow recognitions of what was always there. The planets were visible to ancient humans, but it took millennia to understand that they were worlds like our own, not wandering stars or gods traversing the heavens. The Milky Way was visible to every human who ever lived under dark skies, but only in the past century did we realize it was our galaxy seen edge-on, and that countless other galaxies exist beyond it. Perhaps we're on the verge of another such recognition. The understanding that interstellar traffic has always been flowing through our cosmic neighborhood, and we're only now developing the eyes to see it. What makes this possibility particularly intriguing is that it doesn't require any dramatic changes to our understanding of physics or cosmology. We don't need to invoke faster-than-light travel or exotic technologies. The universe is old, about 13.8 billion years old, and our galaxy has been around for nearly that entire time. That's an enormous span for objects to be set in motion, to be ejected from their home systems and sent on long journeys through interstellar space. Even travelling at relatively modest speeds, far below the speed of light, objects have had ample time to traverse the distances between stars many times over. Consider the comets in our own solar system. Some of them have orbital periods of thousands or even millions of years. They swing out to the very edges of our sun's gravitational influence, so far that the sun appears as merely the brightest star in the sky, and then slowly fall back inward, gaining speed as they approach the inner solar system. Now imagine a comet that gains just a little bit more velocity, perhaps from a close encounter with Jupiter or another planet. Instead of falling back toward the sun, it escapes entirely, becoming an interstellar traveller. This isn't speculation. We know this happens. Our solar system has been launching objects into interstellar space for billions of years, and if our solar system is sending objects out into the cosmos, then every other star system must be doing the same thing. The galaxy becomes not a collection of isolated islands, but an ocean with currents and tides, with objects flowing from one system to another in a vast, slow, ancient circulation. Some of these objects might be natural, comets, asteroids, fragments of planets, but others might be something more. After all, we humans have already sent 5 spacecraft on trajectories that will take them out of our solar system and into interstellar space. Voyager 1 and 2, Pioneer 10 and 11, and New Horizons are all destined to become interstellar travellers, carrying with them artifacts of human civilization. If we, a relatively young technological civilization, have already begun sending objects into interstellar space, how many other civilizations might have done the same over the billions of years of galactic history? This brings us to one of the most tantalizing aspects of the routine visitation hypothesis. If objects from other star systems regularly pass through our solar system, and if even a small fraction of these objects are artificial in origin, then we might be surrounded by artifacts of extraterrestrial intelligence without knowing it. They might be ancient, their creators long extinct, their purposes forgotten. They might be probes, still functioning or long dead, sent out to explore and map the galaxy. They might be something we haven't even conceived of yet, structures or devices that serve purposes we can't imagine with our current understanding of technology and physics. The key word here is might. We're not claiming that alien spacecraft are definitely passing through our solar system. We're simply exploring the possibility, following the logic of what we're beginning to observe about interstellar objects and considering what it might mean. Science progresses not through certainty but through curiosity, through asking, what if? And then carefully, patiently, looking for evidence that might support or refute our hypotheses. And right now, the evidence is intriguing enough to keep us wondering. As your mind drifts with these possibilities, as you feel yourself floating on the edge of sleep and wakefulness, consider how radically our perspective on the cosmos has shifted in just the past few years. In 2016, no human had ever knowingly observed an object from another star system passing through our own. By 2019, we had detected 2 such objects, and astronomers were beginning to realize that these detections might be just the tip of a very large cosmic iceberg. The instruments we use to scan the skies are becoming more sensitive. Our computational abilities are expanding, and our understanding of what to look for is evolving. Each improvement in our capabilities reveals new layers of activity in what we once thought was empty space. The cosmos, it seems, is far busier than we ever imagined. And perhaps that shouldn't surprise us. After all, nature abhors a vacuum, not just in the physical sense, but in the organizational sense as well. Wherever we look in nature, we find flow, exchange, and interaction. Rivers carry sediment from mountains to seas. Winds carry seeds and spores across continents. Ocean currents transport nutrients and organisms around the globe. Birds migrate thousands of miles, connecting distant ecosystems. Why should we expect the cosmos to be any different? Why should we assume that star systems exist in perfect isolation, when everything else we observe in nature involves connection and exchange? Perhaps the most beautiful aspect of this possibility is what it suggests about our future. If interstellar visitation is routine, if objects regularly travel between star systems, then the pathway to the stars might be more accessible than we thought. We don't necessarily need exotic technologies or physics-defying breakthroughs. We might simply need patience, persistence, and the willingness to undertake very long journeys. The cosmos might be traversable not through speed, but through time, not through force, but through gentle persistence. Imagine humanity's distant descendants, perhaps thousands or millions of years from now, living on spacecraft that slowly cruise between the stars. These wouldn't be desperate attempts to escape a dying Earth, but natural extensions of human curiosity and expansion. Just as our ancestors spread across Earth's continents and islands, our descendants might spread across the galaxy, not in a rush, but in a patient, gradual diaspora that unfolds over geological timescales. And if we can imagine such a future for humanity, how many other species might have already embarked on such journeys? The universe might be filled with patient travelers, moving slowly but steadily between the stars. Some might be biological, like us. Others might be artificial intelligences, better suited to the long loneliness of interstellar space. Some might be hybrid beings we can't yet imagine, combinations of biological and technological that transcend our current categories. And some might be so different from us that we wouldn't recognize them as life or intelligence at all, at least not with our current understanding. As you continue to relax, letting these cosmic possibilities wash over you like gentle waves on a peaceful shore, remember that we're not trying to convince you of anything definitive. We're simply exploring, wondering, considering possibilities that emerge from the latest observations and discoveries. Science is as much about questions as answers, as much about wonder as knowledge, and sometimes the most profound insights come not from certainty, but from sitting with uncertainty, from allowing ourselves to dwell in the space between what we know and what we might discover. The idea that interstellar visitors might be routine rather than extraordinary invites us to reconsider almost everything about our cosmic situation. It suggests that isolation might be an illusion created by our limited perception rather than a fundamental reality. It hints that the galaxy might be more like an ecosystem than a collection of isolated worlds, with energy, matter, and perhaps even information flowing between star systems in patterns we're only beginning to perceive. It opens up possibilities for contact and communication that don't require faster than light travel or violations of known physics. But perhaps most importantly, it reminds us that we're still at the very beginning of our cosmic awareness. We've only had telescopes for about 400 years. We've only been able to detect objects in space using radio waves for less than a century. We've only had spacecraft capable of leaving Earth for about 60 years. In cosmic terms, we've barely opened our eyes. We're like infants just beginning to focus on the world around us, still learning to distinguish between what's near and what's far, what's moving and what's still, what's significant and what's background. Every generation of humans has thought they understood the basic structure of the cosmos, and every generation has been proven wrong in fundamental ways. There's no reason to think our generation is any different. We too will likely be looked back upon by future humans as having a quaint, limited understanding of the universe, but that's not a cause for despair, it's a cause for wonder. It means there are still profound discoveries to be made, still revolutionary insights waiting to emerge from patient observation and careful thought. As we prepare to move deeper into this exploration, to examine the evidence and possibilities in more detail, take a moment to appreciate the remarkable position we find ourselves in. We live at a time when humanity is just beginning to detect interstellar visitors, just starting to realize that our solar system might be less isolated than we thought. We're witnesses to a potential revolution in our understanding of our cosmic neighborhood. Future generations might look back on this era as the time when humanity first realized it wasn't alone in the cosmos, not because we detected signals from extraterrestrial intelligence, but because we realized that the galaxy has been sending us visitors all along. The night continues around us, peaceful and deep. Stars wheel overhead in their ancient patterns, following paths that have been stable for millions of years. But among those stable stars, objects are moving, travelling, visiting. Some of them come from unimaginably far away, from star systems whose light takes centuries or millennia to reach us. They carry with them the chemical signatures of alien suns, the isotopic ratios of foreign worlds. They are messengers from the greater galaxy, reminders that we are part of something vast and interconnected. The scale of space is something our minds weren't evolved to comprehend. We developed our intuitions about distance and time in the African savannah, where the horizon might be 20 miles away and a lifetime might span 70 years. But space operates on scales that dwarf these familiar measurements by factors of millions, billions, even trillions. To truly appreciate the possibility of routine interstellar visitation, we first need to wrap our minds around the almost incomprehensible vastness of the cosmos, and paradoxically, understand how this vastness might not be the barrier we once thought it was. Let's begin with something relatively close to home, the distance to our nearest stellar neighbour, Proxima Centauri. This red dwarf star sits about 4.24 light-years away from us. A light year, as you might know, is the distance light travels in 1 year, moving at its cosmic speed limit of about 186,282 miles per second. That works out to roughly 6 trillion miles. So Proxima Centauri is about 25 trillion miles away. These numbers are so large they become meaningless, like trying to understand the federal budget or the number of grains of sand on all the world's beaches. We need better ways to conceptualize these distances. Imagine, if you will, that our solar system is shrunk down to the size of a dinner plate, about 12 inches across. At this scale, Earth would be an invisible speck of dust orbiting about an inch from the center, where the sun would be a grain of sand, so small you'd need a magnifying glass to see it clearly. Neptune, the outermost major planet, would be orbiting at the edge of the plate. Now, at this scale, where would Proxima Centauri be? In the next room? Down the street? The answer might surprise you. At this scale, our nearest stellar neighbour would be another dinner plate about 4 miles away. 4 miles of empty space between dinner plates, each containing a grain of sand surrounded by microscopic dust motes. This is the challenge of interstellar space, the sheer emptiness of it, the vast gulfs of nothing that separate islands of matter. But here's where our perspective starts to shift. That emptiness isn't actually empty. It's filled with particles, fields, radiation, and most importantly for our discussion, it's filled with objects in motion. Every star system is constantly leaking material into interstellar space. Solar winds push particles outward. Gravitational interactions fling comets and asteroids onto escape trajectories. Collisions between objects create fragments that scatter in all directions. The space between stars isn't a void. It's more like a very, very thin soup with occasional chunks floating through it. Now let's expand our view to encompass our entire galaxy, the Milky Way. Our galaxy contains somewhere between 200 and 400 billion stars. We don't know the exact number because many stars are too dim or too obscured by dust for us to detect. These stars aren't distributed randomly, but are organized into a beautiful spiral structure with arms of dense star formation winding out from a central bulge. Our Sun sits in a relatively quiet neighborhood about 26,000 light-years from the galactic center, in a region between 2 major spiral arms known as the Orion Spur. If we could view our galaxy from outside, perhaps from the perspective of someone in the Andromeda Galaxy, our nearest large galactic neighbor, at 2.5 million light-years away, we would see a magnificent spiral about 100,000 light-years across. The visible disk would be relatively thin, perhaps 1,000 light-years thick on average, though the central bulge would be much thicker. Surrounding this visible disk would be a roughly spherical halo of dark matter, ancient stars and globular clusters extending perhaps 300,000 light-years from the center. Within this vast structure, stars aren't stationary. They orbit around the galactic center, taking hundreds of millions of years to complete a single circuit. Our Sun, carrying Earth and all the other planets with it, is racing through space at about 514,000 miles per hour relative to the galactic center. Even at this tremendous speed, it takes us about 230 million years to complete one orbit. The last time Earth was in this position in the galaxy, dinosaurs were just beginning to emerge on our planet's surface. But stars don't just orbit in perfect circles. They also bob up and down through the galactic disk like horses on a cosmic carousel. They have their own individual motions relative to their neighbours, what astronomers call proper motion. Some stars are racing toward us, others away. Some are climbing above the galactic plane, others diving below it. The galaxy is in constant, complex motion, a gravitational ballet involving hundreds of billions of dancers, each following its own path while influenced by all the others. This constant motion has profound implications for interstellar visitation. Stars that are far apart now were once close together. Stars that are neighbours now will drift apart in the future. Over millions and billions of years, our solar system has had different neighbours, different stellar companions on our journey around the galaxy. Each close encounter, and by close, we mean passages within a few light years, provides an opportunity for material to be exchanged between star systems. Consider what happens when two star systems pass relatively close to each other, say within a light year or two. Their gravitational fields interact with the clouds of comets that surround each star, what we call the Oort cloud in our own solar system. These interactions can disturb the orbits of countless comets, sending some plunging toward their parent star and others flying off into interstellar space. Some of these ejected comets will be captured by the passing star system. Others will become interstellar wanderers, drifting through the galaxy until they encounter another star's gravitational field. The Oort cloud itself is a fascinating structure that helps us understand how material might routinely travel between star systems. Extending perhaps a light year or more from our Sun, the Oort cloud contains trillions of icy bodies, remnants from the formation of our solar system 4.6 billion years ago. These objects orbit so far from the Sun that its gravitational grip on them is tenuous. A passing star, or even the gravitational tide of the galaxy itself, can easily perturb their orbits. Some astronomers estimate that our solar system might lose millions of comets to interstellar space every time a star passes within a few light years of us. And stars do pass close to our solar system with surprising regularity. About 70,000 years ago, when our ancestors were first developing complex language and symbolic thought, a binary star system called Schultz's star passed through the outer reaches of our Oort cloud, coming within 0.8 light-years of our Sun. This might seem like ancient history, but in cosmic terms it was yesterday. And Schultz's star wasn't unique. Astronomers have identified several stars that have passed or will pass close to our solar system. In about 1.3 million years, a star called Gliese 710 will pass within 0.1 light-years of us, potentially sending a shower of comets into the inner solar system. These close encounters mean that star systems aren't isolated islands, but are more like ships passing in the night, occasionally coming close enough to exchange cargo. The cargo in this case consists of comets, asteroids, and perhaps other objects we haven't yet imagined. Over the billions of years of galactic history, our solar system has likely experienced thousands of such encounters, each one providing an opportunity for interstellar exchange. But we don't need close stellar encounters for interstellar visitation to occur. Objects ejected from star systems at relatively modest velocities can travel between stars given enough time, and the galaxy has had plenty of time, Our galaxy formed about 13.6 billion years ago, just a few 100 million years after the Big Bang. The oldest stars in our galaxy have been shining for over 13 billion years. That's an enormous span of time for objects to wander between star systems. Let's put this timescale in perspective. If we compressed the entire history of our galaxy into a single year, with the galaxy forming on January 1st, our solar system wouldn't form until August 31st. Life on Earth wouldn't appear until mid-September. Complex multicellular life wouldn't emerge until mid-November. Dinosaurs would rule from December 25th to December 30th. All of human history would occur in the last few seconds before midnight on December 31st. In this compressed timeline, objects ejected from star systems in January would have had 8 months to wander the galaxy before our solar system even formed. This vast timescale changes everything about how we should think about interstellar visitation. An object doesn't need to travel at tremendous speeds to journey between stars. It just needs time. Even moving at speeds we can achieve with current technology, say the 38,000 miles per hour that Voyager 1 is traveling, an object could traverse the distance to Proxima Centauri in about 75,000 years. That might seem like an eternity from a human perspective, but it's nothing in cosmic terms. It's 0.0005% of the galaxy's age. An object ejected from a star system when the galaxy was young could have crossed the entire galaxy multiple times by now. And here's where things get really interesting. The galaxy isn't just old, it's also crowded. Not crowded in the way a city is crowded, but crowded on its own vast scale. Within 50 light-years of our Sun, there are about 133 known star systems containing 188 stars. Many stars come in pairs or groups. Within 100 light-years, there are over 500 star systems. Each of these systems is a potential source of interstellar visitors, and each has been launching objects into interstellar space for billions of years. The cumulative effect of all these star systems ejecting material over billions of years is staggering. Some astronomers estimate that there might be more interstellar objects in our galaxy than there are stars. These objects, comets, asteroids, planets ejected from their systems, and perhaps artificial constructs, form a kind of interstellar sea through which star systems move. We're not sailing through empty space. We're sailing through a sparse but real population of interstellar wanderers. The density of this interstellar population might be much higher than we previously thought. Before we detected Oumuamua, most astronomers expected interstellar objects to be extremely rare in our solar system. But Oumuamua's detection, followed quickly by the discovery of another interstellar visitor, Comet Borisov, suggests that these objects might be passing through regularly. Some calculations suggest that there might be thousands of interstellar objects in our solar system at any given time, most of them too small or too distant for us to detect with current technology. Think about what this means. Right now, as you lie there listening to these words, there might be visitors from other star systems passing through our cosmic neighborhood. They might be ancient comets, older than our Earth, carrying within their icy hearts the chemical signatures of stars that died before our Sun was born. They might be rocky asteroids, fragments of planets that never quite formed, or worlds that were destroyed in cosmic collisions. They might be something else entirely, something our current understanding of planetary formation doesn't account for. The vastness of space, rather than being a barrier to interstellar exchange, might actually facilitate it. The enormous timescales give objects plenty of time to travel between stars. The constant motion of stars through the galaxy ensures that star systems regularly come close enough to exchange material. The sheer number of stars and the billions of years they've been ejecting objects into interstellar space means that space is populated with wanderers. We're not isolated. We're swimming in a sea of interstellar objects, most of them invisible to us, passing through our solar system on journeys that began before our planet existed. This perspective transforms our understanding of our cosmic situation. We're not residents of an isolated island, but inhabitants of a cosmic archipelago, where currents of matter and energy flow between islands over vast timescales. The space between stars isn't empty but filled with travellers, some natural, perhaps some artificial, following paths determined by gravity and chance encounters spanning millions of years. As we contemplate these vast scales of space and time, it's natural to feel small, perhaps even insignificant. But consider this. We are the only known entities in the universe capable of comprehending these scales. Our brains, collections of atoms no different from those in stars and planets, have somehow developed the ability to contemplate distances of billions of light years and timescales of billions of years. We can model the motion of galaxies, predict the paths of comets, and detect objects from other star systems. In all the vast cosmos, as far as we know, we are the only things that know the cosmos exists. This knowledge brings with it a kind of cosmic responsibility. If interstellar visitors are routine, if our solar system regularly receives objects from other stars, then we are not just passive recipients, but active participants in this cosmic exchange. The spacecraft we've sent into interstellar space, the Voyagers, the Pioneers, New Horizons, will someday be interstellar visitors to other star systems. They carry with them not just scientific instruments, but messages, artifacts of human civilization, attempts to communicate across the vast gulfs of space and time. The vastness between worlds, rather than isolating us, connects us to the greater galaxy in ways we're only beginning to understand. Every star we see in the night sky has probably sent us visitors, even if we haven't detected them yet. And our sun has returned the favour, sending comets and perhaps spacecraft to wander among the stars. We're part of a vast, slow, ancient conversation where messages take millions of years to deliver, and responses might come from civilizations that no longer exist. As you drift deeper into relaxation, feeling the weight of your body settling into comfort, imagine yourself not as an isolated being on an isolated world, but as part of this vast cosmic exchange. The atoms in your body were forged in the hearts of stars that died billions of years ago. The water you drink has been cycling through Earth's systems for billions of years and might once have been part of a comet from another star system. You're made of cosmic material, and you are part of cosmic processes that span scales of space and time that dwarf human experience. The vastness between worlds isn't empty space, but a medium through which matter, energy, and perhaps information flow in patterns we're only beginning to perceive. It's a stage for a cosmic drama that has been playing out for billions of years and will continue for billions more. And we, in our brief moment of consciousness, have the privilege of beginning to understand this drama, to see ourselves not as isolated actors, but as part of an ensemble cast that includes every star, planet, comet, and asteroid in the galaxy. On October 19th, 2017, something extraordinary happened. not extraordinary in the sense of dramatic or explosive. There were no cosmic fireworks, no obvious signs that history was being made. Instead, it was extraordinary in its quietness, in the subtle way it suggested that our understanding of our cosmic neighbourhood might need fundamental revision. On that night, astronomer Robert Werrick, using the Pan-STARRS telescope at Haleakala Observatory in Hawaii, detected an object that would challenge our assumptions about how isolated our solar system really is. The object would come to be known as Oumuamua, and it represents humanity's first confirmed observation of an interstellar visitor. Oumuamua, which means scout, or messenger from afar arriving first in Hawaiian, was initially designated as a comet, then reclassified as an asteroid, and finally placed in an entirely new category, interstellar object. But these dry classificatory details don't capture the profound implications of its discovery. For the first time in human history, we had detected something that definitely came from another star system, a visitor from the vast spaces between stars, carrying with it mysteries that we're still trying to unravel. The first unusual thing about Oumuamua was its trajectory. Comets and asteroids in our solar system follow elliptical orbits around the Sun, bound by our star's gravity. But Oumuamua's path was hyperbolic. It was moving too fast to be captured by the Sun's gravity. It had entered our solar system from above the plane of the planets, swooped past the Sun at a distance of about 23 million miles, closer than Mercury's orbit, and was now heading back out into interstellar space, never to return. Its velocity and trajectory indicated that it had come from the direction of the constellation Lyra, though its actual origin was probably much more complex, involving millions or billions of years of wandering through interstellar space. As astronomers around the world turned their telescopes toward this unprecedented visitor, more mysteries emerged. Oumuamua was unlike anything we had seen before in our solar system. It was tumbling end over end, completing a rotation every 7.3 hours. This tumbling motion caused its brightness to vary dramatically, suggesting an extremely elongated shape. Some estimates suggested it might be 10 times longer than it was wide. Imagine a cosmic cigar or needle tumbling through space. No asteroid or comet in our solar system has such an extreme shape, leading to immediate speculation about what could have created such an unusual object. The mysteries deepened as astronomers continued their observations. Despite passing close to the Sun, Oumuamua showed no signs of outgassing, the release of gases that creates the characteristic tail of a comet. This was puzzling, because most objects that come from the outer reaches of a star system contain volatile ices that sublimate when heated by a star. Yet, Oumuamua remained dark and tailless, more like a rocky asteroid than an icy comet. But if it was a rocky asteroid, how did it achieve such an unusual shape? And why was its surface so dark, reflecting only about 4% of the sunlight that hit it? Perhaps the most intriguing mystery emerged as Oumuamua left our solar system. Careful tracking of its trajectory revealed that it was accelerating slightly more than could be explained by the Sun's gravity alone. Something was giving it an extra push, a phenomenon astronomers call non-gravitational acceleration. For comets, this is usually explained by outgassing, jets of gas acting like tiny rockets. But Oumuamua showed no visible signs of outgassing. Various explanations were proposed. Perhaps it was outgas in hydrogen, which would be invisible to our telescopes. Perhaps it was so porous that light pressure from the Sun was pushing it like a solar sail. Or perhaps, And this is where things get really interesting. It was something else entirely. The possibility that Oumuamua might be artificial in origin was raised by serious scientists, most notably by Avi Loeb, the chair of Harvard's astronomy department. Loeb pointed out that Oumuamua's properties were difficult to explain through known natural processes. Its extreme shape, its lack of visible outgassing despite non-gravitational acceleration, its unusual tumbling motion. All of these could potentially be explained if Oumuamua was not a natural object but some kind of artificial construct. Perhaps it was a piece of alien technology, a probe sent to explore other star systems, or even just a piece of cosmic debris from an extraterrestrial civilization. Now, it's important to note that most astronomers don't think Oumuamua was artificial. The scientific consensus leans toward natural explanations, even if we don't fully understand what those explanations might be. But the fact that serious scientists could even entertain the possibility of an artificial origin shows how unusual Oumuamua was, and how much it challenged our preconceptions about interstellar objects. It forced us to confront the reality that we might not be able to easily distinguish between natural and artificial objects passing through our solar system, especially if those artificial objects are ancient, damaged, or designed in ways we don't anticipate. The detection of Oumuamua also forced astronomers to reconsider how common interstellar visitors might be. Before Oumuamua, most models suggested that interstellar objects passing through our solar system should be extremely rare. The fact that we detected one so soon after we developed the capability to do so suggested that they might be much more common than previously thought. If Oumuamua was a once-in-a-lifetime event, it would be an extraordinary coincidence that we happened to detect it just as our survey telescopes became powerful enough to do so. More likely, objects like Oumuamua pass through our solar system regularly, and we're only now developing the technology to notice them. Statistical analyses based on Oumuamua's detection suggest that there might be thousands or even millions of interstellar objects in our solar system at any given time. Most of them would be too small or too distant for us to detect. They would pass through quietly, invisibly, like cosmic ghosts drifting through our neighborhood. Oumuamua itself was only detected because it passed relatively close to Earth and happened to be large enough, estimated at about 650 feet long and 65 feet wide, to reflect enough sunlight for our telescopes to spot it. The discovery of Oumuamua also highlighted how little time we have to study these interstellar visitors. By the time Oumuamua was discovered, it was already heading out of the solar system. Astronomers had only a few weeks to observe it before it became too faint to detect. There was no possibility of sending a spacecraft to intercept it. It was moving too fast and was discovered too late. All we could do was watch it leave, taking its secrets with it. This realization has sparked discussions about how we might better prepare for future interstellar visitors, perhaps even developing spacecraft that could be quickly launched to intercept and study them. Just 2 years after Oumuamua's discovery, astronomers detected a second confirmed interstellar visitor, Comet 2 Borisov, discovered by amateur astronomer Gennady Borisov in August 2019. Unlike Oumuamua, Borisov looked exactly like what we expected an interstellar comet to look like. It had a visible tail, it was outgassing as it approached the sun, and its composition seemed similar to comets from the outer reaches of our own solar system. In many ways, Borisov was reassuring. It showed that not all interstellar objects are as mysterious as Oumuamua. but it also confirmed that interstellar visitors are not extraordinarily rare events. 2 confirmed detections in 2 years suggested that these objects pass through regularly. The contrast between Oumuamua and Borisov is itself instructive. It shows that interstellar objects can vary widely in their properties, just as objects within our own solar system vary from rocky asteroids to icy comets to everything in between. This diversity suggests that interstellar space might be populated with a wide variety of objects, each carrying information about the star system that created it and the journey it has taken through the galaxy. Some might be ancient, dating back to the early days of the galaxy. Others might be relatively young, recently ejected from their home systems. Some might be natural, others might be artificial, and we're only just beginning to develop the ability to tell the difference. The discovery of Oumuamua has also sparked a revolution in how we think about our solar system's history. If interstellar objects pass through regularly now, they must have been passing through for the entire 4.6 billion year history of our solar system. Some of these objects might have been captured by the sun's gravity, becoming permanent residents. There might be asteroids in our solar system right now that originally formed around other stars. Some of the comets in the Oort cloud might be interstellar immigrants. Even some of the meteorites that fall to Earth might have extraterrestrial origins, carrying within them the chemical and isotopic signatures of alien suns. This raises fascinating possibilities about the role of interstellar objects in the development of our solar system, and perhaps even the origin of life on Earth. Some scientists have proposed that life might spread through the galaxy via interstellar objects, a hypothesis called panspermia. Microorganisms protected within rocks or ice might survive the long journey between star systems. If this is true, then life on Earth might have been seeded by an interstellar visitor billions of years ago. We might all be descendants of interstellar immigrants, making us quite literally children of the stars. The cultural impact of Oumuamua's discovery extends far beyond the scientific community. For the first time, humanity had concrete proof that objects from other star systems could visit us. This wasn't science fiction or speculation, it was observed fact. The reality of interstellar visitation, even if only by a probably natural object, has subtly shifted our perspective on our place in the cosmos. We're not as isolated as we thought. The barriers between star systems, while vast, are not impermeable. Exchange between star systems is not only possible, but actually happens. As we continue to monitor the skies, new interstellar visitors will undoubtedly be discovered. Each one will teach us something new about the galaxy we inhabit. Some might be similar to objects in our own solar system, confirming that the processes that formed our planets and comets operate throughout the galaxy. Others might be utterly unlike anything we've seen before, challenging our understanding of planetary formation and stellar evolution. And perhaps, someday, we might detect an interstellar visitor that is unambiguously artificial, a message or messenger from another civilization. The detection capabilities that allowed us to discover Oumuamua are improving rapidly. New telescopes are coming online that will be able to detect smaller and more distant objects. Machine learning algorithms are being developed to automatically scan astronomical data for unusual objects. Networks of telescopes are being coordinated to provide continuous coverage of the sky. Within the next decade, we might be detecting interstellar visitors regularly, perhaps several per year. Each detection will add another piece to the puzzle of understanding our dynamic, interconnected galaxy. Oumuamua's brief passage through our solar system also reminds us of the fleeting nature of cosmic encounters. It was visible to our telescopes for only a few weeks, a blink of an eye in cosmic terms. How many other interstellar visitors have passed through our solar system during human history, unseen and unrecorded? How many passed by while our ancestors looked up at the stars, unaware that some of the points of light were visitors from unimaginably distant places? And how many are passing by right now, too small or too distant for our current instruments to detect? The story of Oumuamua is still being written. Astronomers continue to analyze the data collected during its brief appearance, developing new theories to explain its unusual properties. Some scientists are designing missions that could intercept future interstellar visitors, using spacecraft that could be rapidly launched when a new object is detected. Others are developing new observation techniques that might allow us to detect interstellar objects earlier, giving us more time to study them. The field of interstellar object studies, which didn't exist before 2017, is now a vibrant area of research. As you contemplate Oumuamua's journey, imagine the vast distances it has travelled. Before entering our solar system, it had been wandering through interstellar space for millions, perhaps billions of years. It might have formed in a star system that no longer exists, around a star that died before our sun was born. It might have witnessed the birth and death of multiple star systems during its long journey. And now it continues on, heading toward other stars, other possible encounters. In about 20,000 years, it will pass within a few light years of the star Ross 248. In about 45,000 years, it will be closer to Alpha Centauri than to our Sun. Its journey will continue for billions of years, a silent messenger carrying secrets we barely had time to glimpse. Numbers have a peculiar power to reveal truths that intuition alone cannot grasp. When we apply mathematics to the question of interstellar visitation, patterns emerge that challenge our assumptions about how rare or common such events might be. The equations don't lie, though they can surprise us with their implications. Tonight, let's explore the mathematical framework that suggests interstellar visitation might not be extraordinary but routine, not exceptional but expected, not rare but regular as clockwork operating on cosmic timescales. We begin with one of the most famous equations in astronomy, one that you've probably heard of even if you've never seen it written out, the Drake equation. Formulated by astronomer Frank Drake in 1961, this equation attempts to estimate the number of active, communicating extraterrestrial civilizations in our galaxy. While it was originally designed to think about radio communications, its framework helps us understand the probability of interstellar visitation as well. The equation multiplies together a series of factors: the rate of star formation in our galaxy, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually develops, the fraction of life that becomes intelligent, the fraction that develops communication technology, and the length of time such civilizations release detectable signals into space. When Drake first proposed his equation, many of these factors were complete unknowns. We didn't know if other stars had planets. We didn't know how common Earth-like worlds might be. We had no idea how likely life was to develop given suitable conditions. But in the 6 decades since Drake wrote his equation, we've begun to fill in some of these unknowns with real data, and the results are staggering. We now know that planets are not rare but common. Nearly every star has planets. Many of these planets orbit in the habitable zone where liquid water could exist. The basic chemistry of life, carbon, water, amino acids, exist throughout the galaxy. When we plug reasonable numbers into the Drake equation today, we get estimates ranging from dozens to millions of civilizations in our galaxy alone. But let's set aside the question of intelligent life for a moment and focus on something simpler: the mathematics of objects moving between star systems. Even if life is rare, even if Earth is the only planet in the galaxy with life, the mathematics of orbital mechanics tells us that interstellar exchange of material should be common. Every gravitational interaction between objects in a star system has some probability of ejecting one of those objects into interstellar space. When a comet swings close to a giant planet like Jupiter, it might gain enough velocity to escape the solar system entirely. When two asteroids collide, fragments might be blasted out at escape velocity. When a star dies and explodes as a supernova, it can launch entire planets into interstellar space. Let's work through some numbers to see what this means. Our solar system has been around for about 4.6 billion years. During that time, it has probably ejected millions or billions of objects into interstellar space. These ejections aren't evenly distributed in time. They were probably more common early in the solar system's history, when there were more objects in unstable orbits. But even today, our solar system occasionally ejects comets and asteroids. If we conservatively estimate that our solar system ejects one object per year into interstellar space, and the real number is probably much higher, then over 4.6 billion years we've sent 4.6 billion objects out into the galaxy. Now multiply that by the number of star systems in our galaxy. Let's say 200 billion to be conservative. If each star system has ejected billions of objects over the history of the galaxy, then the total number of interstellar objects in our galaxy could be in the hundreds of trillions or even quadrillions. These objects are spreading through the galaxy, following trajectories determined by their initial ejection velocity and subsequent gravitational encounters. The galaxy becomes not a collection of isolated star systems, but a vast network with countless objects travelling between nodes. The density of interstellar objects depends on how they're distributed through the galaxy. If they were distributed uniformly throughout the galactic disk, the density would be very low, perhaps one object per cubic light-year or less. But interstellar objects aren't distributed uniformly. They follow the gravitational structure of the galaxy, concentrating in regions where stars are denser. They're also not moving randomly, but following orbital paths around the galactic center, just like stars do. This means that certain regions of the galaxy might have much higher densities of interstellar objects than others. When we detected Oumuamua, astronomers were able to work backward from that single detection to estimate the overall density of interstellar objects. The calculation goes something like this. We detected one object of a certain size passing within a certain distance of Earth during a certain period of observation. Given the volume of space we were monitoring and the sensitivity of our instruments, we can calculate how many similar objects must exist for us to have detected one. The answer was surprising. There might be about one interstellar object within the orbit of Earth around the Sun at any given time, and thousands within the orbit of Neptune. These numbers become even more interesting when we consider the cumulative effect over time. If one interstellar object passes within Earth's orbit every year, then over the 4.6 billion year history of our solar system, About 4.6 billion interstellar objects have passed through the inner solar system. Some of these objects might have impacted planets or moons. Others might have been captured into orbit around the Sun. Still others might have had their trajectories altered by gravitational encounters, sending them on new paths through the galaxy. The mathematics of capture is particularly intriguing. When an interstellar object enters our solar system, it typically follows a hyperbolic trajectory that will take it back out into interstellar space. But if that object happens to pass close to a planet at just the right angle and velocity, the planet's gravity can slow it down enough for the Sun to capture it. This process, called gravitational capture, could mean that some of the comets and asteroids we see in our solar system today actually formed around other stars. They're immigrants, naturalized citizens of our solar system that arrived as interstellar visitors and never left. The probability of capture depends on several factors: the object's velocity, its trajectory through the solar system, and the positions of the planets at the time of its passage. Jupiter, with its enormous mass and position in the outer solar system, acts like a gravitational goalkeeper, capturing some interstellar objects while ejecting others. Computer simulations suggest that our solar system might have captured hundreds or thousands of interstellar objects over its history. Some of these captured objects might still be orbiting in the outer solar system, indistinguishable from native comets and asteroids unless we examine them closely. Now let's add another layer of mathematical complexity: the possibility of directed visitation. If even a small fraction of star systems develop intelligent life, and if even a small fraction of those civilizations develop space travel, then the mathematics of interstellar visitation changes dramatically. Instead of random objects following ballistic trajectories, we might have directed probes following optimized paths. These probes wouldn't need to travel at tremendous speeds. Even at a modest 1% of the speed of light, a probe could travel from one star to its nearest neighbor in a few centuries. The mathematics of exponential growth makes the colonization or exploration of the galaxy surprisingly feasible, even with relatively slow spacecraft. This is the basis of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox arises from a simple calculation. If a civilization could travel at just 1% of the speed of light and took 1,000 years to establish a new colony before sending out the next wave of colonization ships, it could colonize the entire galaxy in just 10 million years. That's a long time by human standards, but a blink of an eye in cosmic terms, less than 0.1% of the galaxy's age. This calculation has profound implications for interstellar visitation. If even one civilization in our galaxy developed interstellar travel 1 billion years ago, they could have visited every star system in the galaxy multiple times by now. Their probes or artifacts could be everywhere, including our own solar system. The fact that we haven't detected obvious signs of such visitation is puzzling, leading to various proposed solutions to the Fermi paradox. Perhaps life is extraordinarily rare. Perhaps intelligent life tends to destroy itself. Perhaps advanced civilizations choose not to interfere with developing worlds. Or perhaps, and this brings us back to our central question, visitation is happening, but we haven't recognized it yet. The mathematics of detection is crucial here. Space is vast, and even within our own solar system, we've explored only a tiny fraction of the available volume. If an alien probe were orbiting in the asteroid belt, would we have detected it? Probably not, unless it was very large or actively transmitting signals. We've catalogued only a small percentage of the asteroids in our solar system. There could be thousands of artificial objects mixed in with the natural ones, and we wouldn't know unless we examined each one carefully. Let's consider some specific numbers. The asteroid belt contains millions of objects larger than 1 kilometre in diameter. We've catalogued about 800,000 of them. Of those we've studied in detail, with spacecraft or high-resolution telescopy, fewer than 100. If there were 1,000 artificial objects in the asteroid belt, an enormous number by our standards, the probability of us having detected one by random sampling would be less than 0.01%. The mathematics tells us that we could be swimming in a sea of artificial objects and not know it simply because space is so vast and our exploration so limited. The temporal aspect of the mathematics is equally important. Human civilization has been capable of detecting artificial objects in space for less than a century. That's 0.000002% of the solar system's history. If alien probes visited our solar system regularly, say once every million years, the probability of a visit occurring during the brief window of human technological civilization would be about 0.01%. We could be living in a galaxy where interstellar visitation is routine and still have missed it simply because our window of observation is so narrow. But the mathematics also suggests reasons for optimism about detection. As our observational capabilities improve exponentially, following something like Moore's law, our ability to detect smaller and more distant objects increases dramatically. The Pan-STARRS telescope that detected Oumuamua can survey the entire visible sky every few nights, something that would have been impossible just a few decades ago. The upcoming Vera Rubin Observatory will be even more powerful, capable of detecting objects 10 times fainter than current surveys. If interstellar objects are passing through our solar system regularly, we should detect more and more of them in the coming years. Statistical analysis of the objects we've already detected can tell us about the population we haven't seen yet. This is similar to how ecologists estimate animal populations by capture-recapture methods. If we detect a certain number of interstellar objects of a certain size, we can extrapolate to estimate how many smaller objects must exist. The mathematics suggests an inverse power law. For every large object we detect, there might be hundreds of medium-sized objects and thousands of small ones. The galaxy could be filled with a fine mist of interstellar particles, punctuated by occasional larger objects like Oumuamua. The mathematics of orbital dynamics also tells us where to look for interstellar visitors. Objects entering our solar system from interstellar space will follow predictable trajectories based on their velocity and the Sun's gravity. They're more likely to be detected when they pass close to the Sun, where they're moving fastest and reflecting the most sunlight. There might be certain regions of the sky where interstellar objects are more likely to appear, based on the Sun's motion through the galaxy and the distribution of nearby stars. By focusing our observations on these regions, we can maximize our chances of detection. We can also use mathematics to work backward from observations to origins. By carefully measuring an interstellar object's trajectory, we can calculate where it came from, not its specific star system of origin, which is usually impossible to determine after millions of years of travel, but its general direction and velocity relative to the local stellar neighborhood. This information can tell us about the processes that ejected the object and potentially about the conditions in its original star system. The mathematical models of planetary formation and evolution provide another angle on interstellar visitation. These models predict that young star systems should eject large numbers of planetesimals, small rocky or icy bodies that didn't quite become planets. The models suggest that for every Earth mass planet that forms, several Earth masses of material should be ejected into interstellar space. If this is correct, then interstellar space should be filled with planetesimals from the formation of star systems throughout the galaxy's history. Some of these planetesimals might be quite large, moon-sized or even Mars-sized objects wandering between the stars. Probability theory adds another dimension to our understanding. Even if the probability of any individual interstellar object being artificial is extremely small, say 1 in a billion, the sheer number of objects makes detection of artificial objects almost inevitable given enough time and observation. If quadrillions of interstellar objects exist in our galaxy, and even a tiny fraction are artificial, there could still be millions of artificial objects wandering between the stars. The probability that none of these would ever pass through our solar system is vanishingly small. The mathematics of information theory is also relevant. If advanced civilizations wanted to explore or monitor the galaxy, sending physical probes might be more efficient than trying to communicate by radio. A physical probe can carry vast amounts of information, can make decisions autonomously, and can potentially self-replicate to explore multiple star systems. The energy required to accelerate a small probe to interstellar velocities might be less than the energy required to transmit the same amount of information by radio across interstellar distances. From an information theoretic perspective, interstellar probes might be the optimal way for civilizations to explore and understand the galaxy. As we delve deeper into these mathematical frameworks, patterns emerge that suggest interstellar visitation should not be surprising but expected. The numbers tell us that our solar system should have received many visitors over its history. Some were certainly natural, comets and asteroids ejected from other star systems. But given the age of the galaxy, the number of stars and the possibility of intelligent life, some visitors might have been artificial. The mathematics doesn't prove that artificial interstellar visitors have come to our solar system, but it suggests that it would be more surprising if they hadn't. Perhaps the most unsettling possibility in our contemplation of routine interstellar visitation is not that visitors haven't come, but that they have, and we simply haven't recognized them. Our perception of the cosmos is filtered through human senses evolved for survival on the African savanna. Human minds shaped by terrestrial experience and human assumptions about what alien technology or artifacts might look like. What if interstellar visitors have been passing through our solar system throughout human history? Recorded in astronomical observations we've misinterpreted, visible in phenomena we've explained away, present in our very solar system disguised as natural objects? Tonight, let's explore the possibility that evidence of interstellar visitation might be hidden in plain sight, waiting not for discovery but for recognition. Consider first the limitations of human perception. We see less than 1% of the electromagnetic spectrum. We can't directly perceive magnetic fields, gravitational waves, or the solar wind. Our sense of time is calibrated to human lifespans, making it difficult to perceive processes that unfold over millions of years or happen in microseconds. Our sense of scale is bounded by our physical size, making both the very large and very small almost impossible to truly comprehend. An interstellar visitor using technologies beyond our current understanding might be completely invisible to us, like ultraviolet patterns on flowers invisible to humans but obvious to bees. Throughout history, humans have observed and recorded unusual celestial phenomena that remain unexplained by modern astronomy. Ancient Chinese astronomers, meticulous in their record-keeping, documented guest stars that appeared and disappeared, some of which we now know were supernovae, but others remain mysteries. Medieval chroniclers described strange lights moving across the sky in ways that don't match any known natural phenomena. Indigenous oral traditions from around the world include stories of objects or beings descending from the sky, which we typically interpret as mythology, but which might preserve observations of actual events. Even in the modern era, with our sophisticated instruments and scientific framework, we regularly observe phenomena we can't fully explain. Fast radio bursts, discovered only in 2007, are brief, intense pulses of radio waves from distant galaxies. While natural explanations have been proposed and some sources identified, the mechanism producing these bursts isn't fully understood. Some of them repeat in patterns that seem almost artificial. While most astronomers favour natural explanations, the possibility that some fast radio bursts might be signatures of advanced technology hasn't been completely ruled out. Closer to home, our own solar system is full of anomalies and mysteries that might, and we emphasise might, be evidence of interstellar visitation. Consider the case of Saturn's moon Iapetus, which has a bizarre equatorial ridge that makes it look like a walnut. This ridge, up to 20 kilometers high and running almost perfectly along the moon's equator, has no fully satisfactory natural explanation. Some scientists have speculated, admittedly on the fringes of mainstream astronomy, that such a structure could be artificial, perhaps an ancient artifact from a visiting civilization, or consider the numerous asteroids with unusual properties. The asteroid Bennu, recently visited by NASA's OSIRIS-REx mission, is ejecting particles into space in a way that surprised scientists. The asteroid Psyche appears to be almost entirely metal, possibly the exposed core of a destroyed planet, but its properties don't quite match what we'd expect from natural processes. While natural explanations are certainly more likely, the possibility that some asteroids might be artificial constructs or might contain artificial components can't be definitively ruled out without close examination. The concept of lurkers has been proposed by some scientists, the idea that alien probes might be present in our solar system, observing Earth and humanity without making their presence known. These lurkers wouldn't need to be large or obvious. A probe the size of a smartphone, equipped with advanced sensors and communication systems, could hide among the millions of small objects in our solar system. It could be attached to an asteroid, buried on the moon, or orbiting at a Lagrange point where gravitational forces balance. We would have no way of detecting such an object unless it chose to reveal itself, or we happen to examine its exact location with sufficient precision. Our moon itself presents intriguing mysteries. The lunar surface is covered with unusual features that, while generally explained by impact cratering and volcanism, sometimes challenge our understanding. Transient lunar phenomena, brief flashes of light or colour on the moon's surface, have been observed for centuries. While most are probably caused by impact or electrostatic discharge, some remain unexplained. The moon's far side, hidden from Earth until we sent spacecraft to photograph it, could have harboured artefacts for millions of years without our knowledge. Even now, we've explored less than 1% of the lunar surface in detail. The possibility of ancient artifacts becomes more plausible when we consider the vast timescales involved. If an alien probe arrived in our solar system 1,000,000 years ago, it would predate human civilization by hundreds of thousands of years. Such a probe might still be functioning, or it might be dead, a cosmic fossil waiting to be discovered. On Earth, 1,000,000 years of erosion and geological activity would destroy most artifacts. But in space or on airless bodies like the Moon or asteroids, artifacts could survive for billions of years. Some scientists have proposed searching for such artifacts systematically. The search for extraterrestrial artifacts, CETA, is a complement to the search for extraterrestrial intelligence, SETI. While SETI listens for radio signals from distant civilizations, CETA would search for physical evidence of visitation in our own solar system. This might include unusual isotope ratios that suggest artificial processing, structures that seem too regular to be natural, or objects in orbits that suggest deliberate placement rather than natural capture. The concept of technosignatures has gained traction in recent years. These are observable signatures that would indicate the presence of technology, either in our solar system or around other stars. Technosignatures might include unusual atmospheric, compositions suggesting industrial activity, megastructures partially blocking a star's light, or waste heat from advanced civilizations. In our own solar system, technosignatures might be subtler, unusual concentrations of rare elements, perfectly spherical objects, or materials with properties that don't occur naturally. Historical astronomical observations take on new significance when viewed through this lens. The Great Comet of 1577, observed by Tycho Brahe and others, followed an unusual path and showed variations in brightness that were difficult to explain. While almost certainly a natural comet, it demonstrates how limited our ability to fully characterize such objects was until very recently. How many unusual objects passed through our solar system in centuries past, observed but not understood, their true nature lost to history. Even well-studied objects might harbour secrets. Phobos, the larger moon of Mars, has unusual properties that have led to speculation about its nature. It's less dense than it should be if it were solid rock, suggesting it might be partially hollow. It orbits Mars so closely that tidal forces should have destroyed it long ago, yet it persists. While mainstream science explains these properties through natural processes, Phobos is probably a captured asteroid with a rubble pile structure. The possibility of artificial modification hasn't been definitively disproven. The asteroid belt itself might be a place where interstellar visitors could hide unnoticed. With millions of objects, most of them uncharacterized, an artificial object could easily masquerade as a natural asteroid. It would only need to match the general reflectivity and orbital characteristics of asteroids to avoid detection. Unless we specifically targeted it for close observation, we would never know it was anything other than another space rock. Recent discoveries have shown that our solar system is more dynamic and complex than we previously thought. We've discovered quasi-satellites of Earth, asteroids that follow complex orbits keeping them near our planet. We've found objects with retrograde orbits, moving in the opposite direction to most solar system objects. We've identified asteroids that might be extinct comets, and comets that behave like asteroids. This complexity provides plenty of places for unusual objects to hide, whether they're natural interstellar visitors or something more exotic. The phenomenon of dark comets is particularly intriguing. These are objects that show the orbital characteristics of comets, non-gravitational acceleration suggesting outgassing, but no visible coma or tail. Several such objects have been discovered in recent years. While they're probably comets with unusual compositions or very low activity levels, they demonstrate how objects in our solar system can behave in unexpected ways that challenge our categories and assumptions. Artificial intelligence and machine learning are beginning to revolutionize our ability to search for anomalies in astronomical data. These systems can process vast amounts of observations, identifying patterns or outliers that human astronomers might miss. As we apply these tools to decades of accumulated observations, we might discover that unusual objects have been hiding in our data all along, dismissed as noise or measurement error, but actually representing something significant. The possibility that we might have already detected interstellar visitors without recognizing them extends to meteorites. Every year, tons of material from space falls to Earth. Most of it is from our own solar system, but some meteorites have unusual compositions or isotope ratios that are difficult to explain. While these anomalies are usually attributed to unusual formation conditions or processing in our early solar system, the possibility that some meteorites might have interstellar or even artificial origins can't be completely ruled out. Consider the Hypatia stone found in Egypt in 1996. This small rock has a composition unlike any known meteorite or comet. It contains microscopic diamonds and other minerals that suggest formation under conditions unlike anything in our solar system. While scientists have proposed various natural explanations, none fully account for all of Hypatia's properties. It remains a mystery, a reminder that even objects we can hold in our hands might have origins beyond our current understanding. The concept of panspermia, the idea that life might spread between star systems via meteorites or comets, is relevant here. If microbial life can survive the journey between star systems, then more complex structures might as well. We might have been receiving biological or even technological material from other star systems throughout Earth's history, incorporated into our geology and perhaps even our biology without our knowledge. As we develop more sophisticated techniques for analyzing materials at the atomic and molecular level, we might discover signatures of extraterrestrial origin in objects we've long considered terrestrial. Unusual isotope ratios, impossible molecular structures, or elements in combinations that don't occur naturally could all be techno-signatures hiding in plain sight. The challenge is knowing what to look for and having the technology to detect it. The search for hidden interstellar visitors also raises philosophical questions about the nature of evidence and discovery. How would we recognize an alien artifact if we saw one? Our assumptions about what technology should look like are based on human technology, which has existed for only a few thousand years. Alien technology might be based on principles we haven't discovered, using materials we can't manufacture, serving purposes we can't imagine. It might look nothing like what we expect. This brings us to the concept of cognitive blind spots, limitations in our thinking that prevent us from recognizing certain possibilities. Just as people in the 19th century couldn't conceive of nuclear power or quantum mechanics, we might be unable to conceive of technologies or phenomena that would be obvious to more advanced civilizations. Interstellar visitors might be all around us, but our minds might not be equipped to recognize them as anything other than natural phenomena. Continuing to the natural break point as Chapter 5 approaches its conclusion, The possibility that interstellar visitors might be hidden in plain sight is both exciting and humbling. It suggests that our solar system might be less isolated and more visited than we imagine. It reminds us that our understanding of the cosmos is still primitive, that there might be layers of reality we haven't yet learned to perceive, and it offers hope that as our technology and understanding advance, we might suddenly recognize what has been there all along, evidence that we are not alone, that the galaxy is alive with travelers, and that Earth has been receiving cosmic visitors since long before humanity emerged to wonder at the stars above. As we drift deeper into our cosmic contemplation, let us consider one of the most profound and unsettling solutions to the Fermi paradox, the zoo hypothesis. But tonight, we're going to reimagine it not as a stark barrier between us and the cosmos, but as something more subtle, more nuanced, and perhaps more beautiful. What if Earth isn't isolated in a cosmic zoo, observed but never contacted, but rather exists within a vast nature preserve where visitors pass through regularly, following rules and protocols we don't yet understand? What if the silence we perceive isn't absence but rather a form of cosmic etiquette, a respectful distance maintained by civilizations that understand something about the development of consciousness that we haven't yet grasped? The original zoo hypothesis, proposed by astronomer John Ball in 1973, suggested that advanced extraterrestrial civilizations might deliberately avoid contact with Earth to allow humanity to develop naturally, much as we might observe animals in a wildlife preserve without interfering. It's a compelling idea that explains why we haven't detected obvious signs of extraterrestrial intelligence, despite the mathematical probability that such intelligence should exist. But perhaps this hypothesis needs updating for our current understanding of interstellar dynamics and the evidence we're beginning to accumulate about interstellar visitors. Consider for a moment how we humans approach the study and preservation of uncontacted tribes in remote parts of Earth. We know these tribes exist in the Amazon rainforest, on isolated islands in the Indian Ocean, in the dense jungles of New Guinea. We could easily make contact with them using our technology. We could fly helicopters over their villages, broadcast radio messages they would hear, or simply walk into their territories. But we choose not to, at least officially. We've recognized that contact with technologically advanced civilizations can be devastating for isolated peoples, destroying their cultures, their ways of life, and often their very existence through disease and social disruption. Now imagine this principle extended to a galactic scale. Advanced civilizations that have existed for millions or billions of years might have learned through experience, perhaps tragic experience, that premature contact with developing civilizations causes more harm than good. They might have established protocols, agreements, or even enforced laws about how to interact or not interact with worlds like Earth. These protocols might not prohibit all visitation, but might govern how such visits are conducted, what traces can be left, and what kinds of observations are permitted. In this reimagined zoo hypothesis, Earth isn't surrounded by an impermeable barrier, but rather exists within a managed space where certain activities are permitted and others are not. Interstellar objects might pass through our solar system regularly, as we're beginning to observe, but artificial probes might be programmed to remain undetectable, to self-destruct if discovered, or to masquerade as natural objects. The goal wouldn't be to isolate us completely, but to allow us to develop at our own pace, making our own discoveries, learning about the universe through our own efforts rather than having knowledge handed to us before we're ready to understand its implications. This perspective transforms the zoo hypothesis from a prison into something more like a cosmic nursery, where young civilizations are given space and time to grow, make mistakes, learn, and eventually mature to the point where they can join the galactic community as equals rather than as dependents. The visitors passing through our solar system might be monitoring our progress, ensuring our safety from genuine cosmic threats, or simply passing through on their own journeys while being careful not to disturb our development. The beauty of this reimagined hypothesis is that it aligns with what we're actually observing. We're detecting interstellar visitors like Oumuamua and Borisov, objects that seem natural but have properties that push the boundaries of our understanding. If advanced civilizations wanted to observe Earth without revealing themselves, sending probes disguised as natural objects would be an elegant solution. These probes could gather information, transmit it back to their creators via methods we can't detect, and continue on their way, leaving us none the wiser. Consider the technological possibilities available to a civilization even just 1,000 years more advanced than us. They might have developed materials that perfectly mimic the spectroscopic signatures of natural asteroids or comets. They might have propulsion systems that leave no detectable exhaust or energy signature. They might communicate using neutrinos, gravitational waves, or quantum entanglement. Methods that we've only recently discovered exist and can barely detect even when we're looking for them. A probe using such technologies could orbit in our solar system for millions of years, observing Earth's evolution, and we would never know it was there unless it chose to reveal itself. The reimagined zoo hypothesis also suggests that the galaxy might be divided into zones or regions with different levels of protection or management. Earth might be in a region designated for minimal interference, where natural processes are allowed to unfold with only subtle guidance or protection. Other regions might be more actively managed, with regular contact between civilizations. Still others might be quarantine zones, areas where dangerous experiments are conducted, or where civilizations that pose a threat to others are contained. This cosmic zoning would create a structured galaxy, where different rules apply in different regions, all managed by consensus or authority structures we can't yet imagine. Think about how this might work in practice. When an interstellar object approaches our solar system, it might receive a signal, undetectable to us, informing it of our protected status. Natural objects would continue on their paths unchanged, but artificial probes might adjust their trajectories to avoid close approaches to Earth, or they might activate stealth systems to ensure they remain undetected. This would create a filter effect, where we see natural interstellar visitors but not artificial ones, giving us a skewed perception of what's actually passing through our neighborhood. The protocols governing visitation might be incredibly sophisticated, developed over millions of years of galactic history. They might specify minimum approach distances, maximum observation durations, prohibited technologies, and required safety measures. There might be penalties for violating these protocols, exclusion from galactic communication networks, loss of access to shared scientific knowledge, or even active enforcement by some kind of galactic authority. The fact that we haven't detected obvious alien visitors might not mean they haven't come, but rather that they're following rules designed to protect us. This reimagined hypothesis also addresses one of the main criticisms of the original zoo hypothesis: the difficulty of maintaining perfect isolation over millions of years and across potentially millions of civilizations. Perfect isolation would indeed be nearly impossible to maintain, but imperfect isolation, where occasional visitors pass through while following certain guidelines, will be much easier to sustain. It would allow for the kind of subtle contact that doesn't disrupt development, but might provide gentle guidance or protection when necessary. Consider the possibility that Earth has been receiving subtle assistance throughout its history. Mass extinction events that should have wiped out all life might have been mitigated by unseen intervention. Asteroid impacts that would have reset evolution might have been deflected just enough to miss. The emergence of life itself, or the development of intelligence, might have been gently encouraged at critical moments. We would never know about such interventions because they would be designed to appear natural, to preserve the integrity of our development while ensuring our survival. The reimagined zoo hypothesis also suggests that contact might not be a binary state, either complete isolation or full communication, but rather a gradual process that unfolds as a civilization matures. We might be receiving increasingly obvious signs of extraterrestrial presence as we develop the capability to detect and understand them. The discovery of interstellar objects might be part of this process, a gentle introduction to the reality that our solar system isn't isolated but is part of a busy galactic community. As we develop more sophisticated detection methods, we might discover more evidence of visitation, each discovery preparing us for the next level of awareness. This gradual revelation might explain some of the patterns we're seeing in our discoveries. First, we discover that planets exist around other stars, something that expands our perspective without directly challenging our uniqueness. Then we discover that Earth-like planets are common, suggesting that life might exist elsewhere. Now we're discovering that interstellar objects visit our solar system, showing that exchange between star systems is possible. Each discovery builds on the previous ones, gradually preparing us for the possibility that we're not alone, that the galaxy is inhabited, and that visitors have been passing through our neighborhood all along. The psychological and sociological wisdom behind such a gradual approach becomes apparent when we consider how humanity has historically responded to paradigm shifts. The Copernican revolution, which moved Earth from the center of the universe to just another planet orbiting the sun, took centuries to be fully accepted and caused enormous social and religious upheaval. The theory of evolution, which connected humans to all other life on Earth, is still rejected by significant portions of the population more than 150 years after Darwin. The discovery that we're not alone in the universe, that we're being observed, and that we're part of a managed cosmic preserve would be the ultimate paradigm shift, one that needs to be introduced gradually to avoid catastrophic social disruption. The reimagined zoo hypothesis also provides a framework for understanding why different people have such different experiences and beliefs about extraterrestrial contact. If visitation is happening but is being carefully managed to remain ambiguous, then some people might have experiences that seem to indicate contact, while others see no evidence at all. The ambiguity itself might be intentional, allowing those who are ready to consider the possibility of extraterrestrial presence to do so, while not forcing the reality on those who aren't prepared for it. This creates a kind of self-selecting disclosure, where humanity gradually becomes aware of extraterrestrial presence at a pace determined by our collective readiness rather than by external imposition. The role of consciousness and perception in this hypothesis is particularly intriguing. Advanced civilizations might understand aspects of consciousness that we haven't yet discovered. They might know that consciousness isn't just a passive observer of reality, but plays an active role in shaping it. They might be able to influence our perception in ways that make their presence undetectable to those who aren't ready to perceive it. This isn't magic or mysticism, but could be based on scientific principles we haven't yet discovered. Just as electromagnetic radiation was unknown to humans for most of our history despite surrounding us always. Consider how this might relate to the many reported UFO sightings and alleged contact experiences throughout human history. While most of these can be explained by natural phenomena, misidentification, or psychological factors, the reimagined zoo hypothesis suggests that some might represent genuine observations of visiting probes or craft that briefly became visible due to malfunction, deliberate revelation, or the observer's unusual perceptual state. The visitors might usually be invisible to us, not because they're using advanced cloaking technology, but because they're operating in a way that our consciousness typically doesn't register, like background noise we've learned to ignore. The implications of this reimagined zoo hypothesis for our future are profound. If we're being observed and protected, it means we're not alone in facing the challenges of technological development. Other civilizations have presumably passed through the dangerous transition we're currently navigating, where we have the power to destroy ourselves but haven't yet developed the wisdom to ensure we don't. The fact that we're still here, despite nuclear weapons, climate change, and other existential threats, might not be entirely due to luck. We might have guardian angels of a sort, advanced civilizations that intervene subtly to prevent our self-destruction while allowing us to learn from our mistakes. This protection, if it exists, probably has limits. The protectors might prevent us from completely destroying ourselves, but allow smaller catastrophes that serve as learning experiences. They might deflect planet-killing asteroids, but allow smaller impacts that advance our understanding of cosmic threats. They might prevent nuclear war from ending civilization, but allow limited conflicts that teach us the horror of such weapons. This balanced approach would preserve our species while maintaining our autonomy and responsibility for our own development. The reimagined zoo hypothesis also suggests that our cosmic quarantine, if we can call it that, is temporary. At some point, if we survive and mature as a species, we'll presumably graduate from the cosmic nursery and join the galactic community. The signs of this approaching graduation might already be visible. Our rapid technological development, our growing awareness of existential risks, our beginning exploration of space, and our discovery of interstellar visitors might all be indicators that we're approaching a threshold. The next century or two might be critical, determining whether we're ready for broader contact or need more time in protective isolation. What might trigger the end of our isolation? Perhaps it will be our development of certain technologies, fusion power, artificial general intelligence, or interstellar travel capability. Perhaps it will be our achievement of certain social milestones, the end of warfare, the establishment of a united planetary government, or the development of a truly sustainable civilization. Or perhaps it will be our discovery of the observers themselves, proving that we've developed the perceptual and technological sophistication to recognize what has been hidden in plain sight. The beauty of the reimagined zoo hypothesis is that it transforms our apparent cosmic loneliness from abandonment into care. We're not isolated because we're unimportant or because nobody knows we're here. We're given space because our development matters, because our unique perspective and solutions to existence's challenges are valued, because diversity of thought and culture is recognized as important on a galactic scale. Every civilization might go through this phase, developing in partial isolation until they're ready to contribute to the galactic community as equals. As you lie there contemplating these possibilities, consider how this perspective changes our relationship with the cosmos. We're not strangers in a hostile or indifferent universe, but children in a cosmic nursery, surrounded by patient elders waiting for us to grow up enough to join them. The stars aren't distant and unreachable, but are homes to neighbours we haven't yet met. The interstellar visitors passing through our solar system might be more than random wanderers. They might be gentle check-ins, subtle reminders that we're part of something larger, breadcrumbs on a trail leading to a future we can barely imagine. Every passage through space leaves traces, however faint they might be. Just as a ship leaves a wake in water that persists long after the vessel has passed, objects moving through our solar system create disturbances in the fabric of space-time, in the distribution of particles and fields, in the very structure of our cosmic neighborhood. Tonight, let us explore these signatures, these subtle marks left by interstellar visitors that might be detectable if we know how to look for them. We're entering the realm of cosmic forensics, where patient observation and careful analysis might reveal evidence of visitations that occurred long before humans existed, or that are happening right now in ways we're only beginning to learn how to perceive. The gravitational signatures of passing objects are perhaps the most fundamental traces left behind. Every object with mass warps space-time around it, creating a gravitational field that extends infinitely outward, growing weaker with distance but never truly disappearing. When an interstellar visitor passes through our solar system, it doesn't just follow a path determined by the sun's gravity, it also exerts its own gravitational influence on everything around it. Planets are pulled slightly from their orbits, asteroids are nudged onto new trajectories, and comets in the distant Oort cloud feel a gentle tug that might alter their paths by tiny amounts. These gravitational perturbations are usually too small to detect directly, especially for objects the size of Oumuamua or smaller. But their cumulative effects over time can be significant. Every interstellar visitor that has passed through our solar system over the past 4.6 billion years has left its gravitational fingerprint on the orbits of our planets, asteroids, and comets. The current structure of our solar system, the precise orbits of the planets, the distribution of asteroids, the population of comets, has been shaped in part by these encounters. We're looking at a palimpsest, a document that has been written over many times, where each layer of writing influences the next. Modern computational power allows us to run sophisticated simulations that can work backward from the current state of our solar system to infer past gravitational interactions. By carefully measuring the orbits of thousands of asteroids and comets, astronomers can detect anomalies that suggest past encounters with massive objects. Some of these anomalies might be explained by interactions with known planets, but others might require the passage of interstellar visitors to fully account for the observed orbital distributions. It's like being a detective at a crime scene, using the position of objects to reconstruct events that happened long ago. The Oort cloud, that vast sphere of icy bodies surrounding our solar system, at distances of up to a light year from the Sun, is particularly sensitive to gravitational perturbations from passing objects. The comets in the Oort cloud are so loosely bound to the Sun that even a small gravitational nudge can dramatically alter their orbits. Some astronomers have suggested that the current structure of the Oort cloud shows evidence of past stellar encounters, times when other stars passed close enough to our solar system to scatter comets, like leaves in a cosmic wind. But stars aren't the only objects that could create such disturbances. A massive interstellar visitor, perhaps a rogue planet, ejected from another star system, could create similar patterns. The distribution of long-period comets, those that take thousands or millions of years to orbit the Sun, provides another set of clues. These comets fall toward the Sun from the Oort cloud, and their orbital parameters contain information about what sent them on their current paths. Statistical analysis of long-period comet orbits has revealed asymmetries and clustering that suggest past gravitational perturbations. While some of these patterns can be explained by the gravitational influence of the giant planets or the galactic tide, others remain mysterious. They might be signatures of interstellar visitors that passed through our solar system thousands or millions of years ago, their gravitational influence still echoing in the orbits of comets we observe today. Beyond gravitational signatures, interstellar visitors might leave electromagnetic traces. Any object passing through our solar system is bombarded by solar radiation and the solar wind, streams of charged particles flowing outward from the Sun. This interaction can cause the object to develop an electric charge, emit radiation, or alter the local magnetic field. While these effects are usually weak and temporary, sensitive instruments might be able to detect them. The disturbance in the solar wind caused by Oumuamua's passage, for instance, was too small for our current instruments to detect, but future space-based observatories might be able to sense such disturbances. The interaction between interstellar visitors and the solar wind might also create more persistent signatures. When the solar wind hits an object, some particles are reflected, others absorbed, and the flow pattern is disrupted. This creates a wake downstream from the object that can persist for millions of miles. If an interstellar visitor passed through the inner solar system, it might have created disturbances in the solar wind that affected the space weather around Earth and other planets. These effects would be recorded in the geological record, in the isotopic composition of lunar samples, in the magnetic orientation of Earth rocks, in the chemistry of ancient ice cores. Consider the possibility of exotic matter signatures. If some interstellar visitors are artificial in origin, they might be composed of materials that don't naturally occur in our solar system. These materials might have unusual isotopic ratios, impossible molecular structures, or elements in combinations that require artificial processing to create. If such an object collided with an asteroid or moon in our solar system, it might have left traces of exotic matter that we could detect. Some scientists have proposed searching for such signatures in lunar craters, where the lack of atmosphere and geological activity would preserve evidence of ancient impacts. The temporal dimension of these signatures is particularly fascinating. Space isn't just three-dimensional, it's four-dimensional, with time as the fourth dimension. Events that happened millions or billions of years ago still influence the present through chains of cause and effect that propagate through time. An interstellar visitor that passed through our solar system when it was young might have influenced the formation of the planets, the delivery of water to Earth, or even the origin of life. We might owe our very existence to gravitational nudges from ancient interstellar visitors that altered the trajectory of comets carrying organic molecules or water. The search for technosignatures, signs of advanced technology, in our solar system represents a new frontier in the search for evidence of interstellar visitation. These signatures might be incredibly subtle. Advanced technology might leave traces in the form of unusual isotope ratios from nuclear processes, microscopic artifacts that could only be created through nanotechnology, or patterns in the distribution of asteroids that suggest mining or resource extraction. The challenge is distinguishing these potential technosignatures from natural phenomena, especially when we don't know what advanced alien technology might look like. One intriguing possibility is that interstellar visitors might leave information signatures, messages or data encoded in ways we're only beginning to learn how to detect. Information can be encoded in many ways, in the modulation of electromagnetic radiation, in the quantum states of particles, in the arrangement of matter at the molecular or atomic level. An advanced civilization might encode messages in the trajectory of a probe, in its rotation rate, in its surface composition, or in ways we haven't yet imagined. The discovery of Oumuamua's unusual acceleration, for instance, could potentially be interpreted as a signature, though most scientists favour natural explanations. The quantum realm offers particularly exotic possibilities for signatures. Quantum entanglement, the phenomenon where particles remain connected regardless of the distance between them, might be used by advanced civilizations for communication or navigation. An interstellar probe might carry entangled particles that allow it to communicate instantaneously with its home system, leaving quantum signatures in our solar system that we don't yet know how to detect. As our understanding of quantum mechanics improves and our ability to manipulate quantum states advances, we might discover that space is filled with quantum signatures of advanced technology. Time itself might carry signatures of interstellar visitation. General relativity tells us that massive objects and high velocities can alter the flow of time. An interstellar visitor travelling at a significant fraction of the speed of light would create relativistic effects, tiny distortions in space-time that might be detectable with sufficiently sensitive instruments. These temporal signatures would be incredibly subtle, perhaps only detectable through their cumulative effects on the orbits of planets and asteroids over millions of years. But they would be unique signatures that couldn't be mimicked by natural phenomena. The interstellar medium itself, the gas and dust between stars, might preserve signatures of objects passing through it. When an interstellar object travels through this medium at high speed, it creates a shock wave, compressing the gas and dust, heating it, and potentially triggering chemical reactions. These disturbances can persist for thousands of years, slowly expanding and fading but potentially detectable with sensitive instruments. Radio telescopes might detect faint emissions from these disturbances. Infrared telescopes might see the heat they generate, and spectroscopic analysis might reveal unusual chemical compositions created by the passage of artificial objects. Our improving ability to detect gravitational waves opens up entirely new possibilities for detecting signatures of interstellar visitors. While the gravitational waves from something like Oumuamua would be far too weak for our current detectors, more massive objects or those travelling at higher speeds might produce detectable signals. Future space-based gravitational wave observatories might be able to detect the passage of massive interstellar objects through our solar system in real time, or even detect the signatures of such passages that occurred in the past, but whose gravitational waves are only now reaching us. The asteroid belt might be particularly rich in signatures of past interstellar visitors. If artificial probes have been passing through our solar system for millions or billions of years, some of them might have malfunctioned, collided with asteroids, or deliberately anchored themselves to asteroids for long-term observation. The asteroid belt would be an ideal hiding place for such artifacts: stable orbits, protection from solar radiation, and access to raw materials for self-repair or replication. Some of the unusual properties we observe in certain asteroids might be signatures of artificial modification or the presence of attached artifacts. The concept of sentinel objects is particularly intriguing. These would be artificial objects placed in our solar system specifically to monitor Earth and humanity, activating or revealing themselves only when certain conditions are met. They might be programmed to remain completely passive and undetectable until humanity reaches a certain level of technological development, at which point they begin transmitting signals or otherwise revealing their presence. The signatures of such objects might be designed to be discoverable only when we develop specific technologies or reach certain milestones in our understanding of physics. Biological signatures represent another category of potential evidence. If life can spread between star systems, either naturally through panspermia or artificially through directed panspermia, then interstellar visitors might carry biological material. This material might be preserved in meteorites, in the ice of comets, or even integrated into Earth's biosphere. Unusual genetic sequences, proteins that don't fit standard evolutionary patterns, or organisms with inexplicable characteristics might be signatures of biological material delivered by interstellar visitors. The recent discovery of complex organic molecules in interstellar space and on comets makes this possibility more plausible. The signatures we're discussing might not be independent, but could form patterns that reinforce each other. A gravitational anomaly in asteroid orbits might correlate with unusual isotope ratios in the same region. Electromagnetic disturbances might coincide with the calculated passage times of interstellar objects. Biological anomalies might appear shortly after impact events that could have been caused by interstellar visitors. By looking for these correlations, we might be able to build a stronger case for past visitation than any single line of evidence could provide. Our technology for detecting these signatures is improving exponentially. Machine learning algorithms can sift through vast amounts of astronomical data, identifying subtle patterns that human observers might miss. Quantum sensors can detect incredibly small disturbances in electromagnetic and gravitational fields. Space-based telescopes can observe without the interference of Earth's atmosphere, detecting fainter objects and subtler signatures. As these technologies continue to advance, we might suddenly find ourselves able to read signatures that have been there all along, like developing the ability to see colours that were always present, but previously invisible to us. The philosophical implications of these signatures are profound. If we can detect evidence of past interstellar visitors, it means our solar system has a history of contact with the wider galaxy. We're not living in pristine, untouched space, but in a cosmic crossroads that has seen countless travellers over billions of years. Every signature we detect is a thread connecting us to the greater galaxy, a reminder that our story is part of a much larger narrative that spans space and time on scales we're only beginning to comprehend. Revolutions in human understanding rarely announce themselves with fanfare. They don't arrive as sudden revelations that instantly transform our worldview, but rather as slow accumulations of evidence, gradual shifts in perspective, and quiet realizations that what we once thought impossible has become not just possible, but probable. Tonight, we find ourselves in the midst of such a quiet revolution, a fundamental shift in our understanding of Earth's relationship with the cosmos, unfolding not through dramatic discoveries, but through the patient accumulation of observations that suggest our cosmic neighborhood is far busier than we ever imagined. This revolution began not with the detection of alien signals or the landing of extraterrestrial visitors, but with the gradual realization that the boundaries we imagined between star systems are more porous than we thought. It started with improvements in our telescopes that allowed us to detect smaller and fainter objects, with computer algorithms that could process vast amounts of data to find subtle anomalies, with theoretical models that showed interstellar exchange was not just possible but inevitable. Each small step forward in our capabilities revealed new layers of activity in what we once thought was empty space. Consider how our understanding of the solar system itself has evolved over just the past few decades. When the Voyager spacecraft were launched in 1977, we thought the solar system had 9 planets and a relatively simple structure. Now we know about the Kuiper Belt, a vast region beyond Neptune filled with icy bodies. We've discovered the scattered disk, an even more distant population of objects on eccentric orbits. We've found that Pluto is just one of many dwarf planets, and that the outer solar system is populated with countless small worlds we're only beginning to catalogue. Each discovery has made our cosmic neighbourhood seem less empty, more dynamic, more connected to the space beyond. The detection of exoplanets represents another thread in this quiet revolution. For most of human history, we could only speculate about whether other stars had planets. The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995. Now, less than 3 decades later, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting confirmation. We've learnt that planets are not rare but ubiquitous, that nearly every star has planets, that Earth-like worlds are common. This transformation from speculation to certainty happened so gradually that we've barely noticed how radically it has changed our cosmic perspective. The discovery that water is common throughout the solar system and the galaxy represents another quiet shift in understanding. We once thought Earth was unique in having liquid water, but we've discovered that Jupiter's moon Europa has a subsurface ocean containing more water than all of Earth's oceans combined. Saturn's moon Enceladus shoots geysers of water into space from its own hidden ocean. Mars once had rivers and lakes, and might still have liquid water underground. Water ice is common on asteroids and comets. Organic molecules, the building blocks of life, are found throughout the solar system and in interstellar space. The ingredients for life, we're learning, are not rare but abundant. The paradigm shift regarding interstellar visitors is perhaps the most recent and subtle aspect of this revolution. Before 2017, the idea that objects from other star systems might pass through our solar system was purely theoretical. The detection of Oumuamua changed that from hypothesis to observed fact. The subsequent detection of Comet Borisov confirmed that such visits are not extraordinarily rare. Now astronomers are developing models suggesting that interstellar objects might be passing through our solar system regularly, perhaps several times per year. We're not witnessing isolated events, but discovering an ongoing process that has been happening throughout the solar system's history. This quiet revolution extends to our understanding of life itself. The discovery of extremophils, organisms that thrive in conditions once thought incompatible with life, has expanded our concept of habitability. We've found life in boiling water, in highly acidic environments, in the depths of the ocean where no sunlight penetrates, even inside rocks miles beneath Earth's surface. Some organisms can survive exposure to the vacuum and radiation of space. These discoveries suggest that life might be far more adaptable and widespread than we imagined, able to survive journeys between star systems and establish itself in environments we once thought sterile. The development of new detection technologies is accelerating this quiet revolution. The James Webb Space Telescope is revealing the universe in unprecedented detail, detecting the atmospheres of exoplanets and the composition of interstellar objects. Ground-based telescopes with adaptive optics can now achieve resolutions that rival space telescopes. Networks of small telescopes working together can monitor the entire sky continuously. Gravitational wave detectors have opened an entirely new window on the cosmos. Each technological advance reveals phenomena that were always there but previously invisible to us. Artificial intelligence and machine learning are transforming our ability to process and understand astronomical data. These systems can identify patterns in vast datasets that would take human astronomers centuries to analyze. They can detect subtle anomalies that might indicate unusual objects or phenomena. They can simulate complex gravitational interactions to predict where interstellar visitors might appear, or to trace back where they came from. AI is becoming a crucial tool in our quest to understand our cosmic neighborhood, revealing connections and patterns we couldn't see before. The sociological aspect of this quiet revolution is equally important. Public perception of extraterrestrial life and interstellar phenomena has shifted dramatically over the past few decades. What was once relegated to science fiction and fringe beliefs has become mainstream scientific discussion. Government agencies that once dismissed UFO reports now acknowledge unidentified aerial phenomena and fund research to understand them. Scientists who once risked their careers by discussing extraterrestrial intelligence now openly speculate about technosignatures and alien artifacts. The stigma associated with these topics is gradually eroding, allowing for more open and rigorous investigation. The interdisciplinary nature of this revolution is bringing together fields that rarely interacted before. Astronomers are working with biologists to understand how life might survive in space. Geologists are collaborating with physicists to identify potential technosignatures in geological samples. Computer scientists are partnering with astronomers to develop algorithms for detecting unusual objects. Philosophers are engaging with scientists to explore the implications of potential contact. This cross-pollination of ideas is generating insights that no single discipline could achieve alone. Our understanding of timescales is undergoing a particularly profound shift. Human civilization has existed for such a brief moment in cosmic history that we've tended to think of the universe as static, unchanging, except for dramatic events like supernovae. But we're beginning to appreciate that the cosmos is constantly in flux on timescales just beyond human perception. Star systems drift past each other, exchanging material. Galactic orbits bring different stellar neighborhoods into proximity. What seems permanent on human timescales is transient on cosmic ones. This expanded temporal perspective is essential for understanding phenomena like routine interstellar visitation. The concept of the Great Filter has become central to discussions about life in the universe and our own future. This hypothetical barrier prevents most life from developing into spacefaring civilizations. The quiet revolution in our understanding suggests that if we've passed the Great Filter, we might not be alone, but rather late arrivals to a galaxy already populated with travelers. If the Great Filter lies ahead of us, the apparent absence of obvious alien civilizations might be a warning about challenges we've yet to face. Either way, our evolving understanding of interstellar phenomena informs our perspective on humanity's future. Cultural narratives about our place in the universe are slowly shifting to accommodate these new understandings. The idea that Earth is a visited world, that our solar system regularly receives interstellar guests, is percolating through society in subtle ways. Science fiction is becoming more sophisticated in its treatment of interstellar travel and alien contact. Educational curricula are beginning to include discussions of exoplanets and astrobiology. Museums are creating exhibits about interstellar objects and the search for extraterrestrial intelligence. These cultural shifts prepare society for potential future discoveries while making the current quiet revolution more visible. The economic implications of this revolution are beginning to emerge. Investment in space technology is accelerating, driven partly by the growing awareness that space might be less empty and more accessible than we thought. Companies are developing technologies to mine asteroids, which might include interstellar visitors with exotic compositions. Research into advanced propulsion systems is increasing, motivated by the possibility that interstellar travel might be more feasible than previously believed. The space economy is expanding beyond satellites and launches to encompass possibilities that seemed like fantasy just a few years ago. The philosophical implications of this quiet revolution are perhaps the most profound. We're moving from a worldview where Earth is isolated and possibly unique to one where we're part of a dynamic, interconnected galaxy. This shift affects fundamental questions about the nature of life, intelligence, and our purpose in the universe. If interstellar visitation is routine, if life is common, if intelligence emerges regularly throughout the galaxy, then humanity's role might not be as central characters, but as part of an ensemble cast in a cosmic drama we're only beginning to understand. The role of consciousness in this revolution deserves special attention. As we expand our awareness of cosmic phenomena, we're also expanding our consciousness as a species. We're developing what might be called a cosmic consciousness, an awareness of ourselves as part of a larger galactic community, even if we haven't yet made direct contact with other members. This expansion of consciousness might be a necessary precursor to actual contact, preparing us psychologically and culturally for the reality of not being alone. The scientific method itself is evolving to accommodate these new perspectives. Traditional astronomy focused on observation and theory, but the study of interstellar visitors and potential techno-signatures requires new approaches. We need to develop methods for distinguishing artificial from natural objects when we don't know what alien technology might look like. We need statistical frameworks for evaluating evidence that might be deliberately ambiguous. We need protocols for potential contact that balance scientific openness with appropriate caution. The quiet revolution is not just in what we know, but in how we approach knowing. Educational systems are beginning to adapt to this changing understanding, though slowly. Astronomy courses that once focused solely on stellar evolution and cosmology now include sections on exoplanets and astrobiology. Biology courses discuss extremophiles and the possibility of non-terrestrial life. Chemistry courses explore the organic molecules found in space and their potential role in the origin of life. This educational evolution ensures that future generations will grow up with a fundamentally different cosmic perspective than their predecessors. The media's treatment of these topics has evolved significantly. News outlets that once treated any discussion of extraterrestrial phenomena as fringe now regularly report on discoveries of exoplanets, interstellar objects, and the search for technosignatures. Documentaries explore these topics with scientific rigor rather than sensationalism. Podcasts featuring serious scientists discussing the possibility of extraterrestrial intelligence attract millions of listeners. This media evolution both reflects and drives the quiet revolution in public understanding. International cooperation in space exploration and the search for extraterrestrial phenomena is increasing. Countries that were once rivals in space are now collaborating on missions and sharing data. The detection of interstellar visitors has become a global effort, with observatories around the world coordinating their observations. Protocols for potential contact are being discussed at international levels. This cooperation suggests a growing recognition that the questions we're exploring transcend national boundaries and require humanity to work together. The development of new theoretical frameworks is accelerating our understanding. Scientists are proposing new models for how civilizations might develop and interact on galactic scales. Theories about the distribution and behavior of interstellar objects are becoming more sophisticated. Frameworks for understanding potential technosignatures are being refined. These theoretical advances provide the conceptual tools needed to interpret observations and guide future research. As we continue through this quiet revolution, patterns are emerging that suggest we're approaching a threshold. The acceleration of discoveries, the convergence of multiple lines of evidence, the growing cultural acceptance of cosmic phenomena, all point toward a potential tipping point where quiet revolution becomes explicit transformation. We might be the generation that witnesses humanity's transition from cosmic isolation to cosmic awareness, from wondering if we're alone to knowing we're part of a vast community of worlds. The beauty of this quiet revolution is that it's happening through the accumulation of scientific evidence rather than through revelation or speculation. Each discovery builds on previous ones, creating a robust framework of understanding that becomes harder to dismiss or ignore. We're not being told that interstellar visitors are routine. We're discovering it through careful observation and analysis. We're not being convinced that life might be common. We're finding the evidence that suggests it is. This revolution is also democratizing in nature. The data supporting these new understandings is increasingly available to anyone with internet access. Amateur astronomers can contribute to the detection of interstellar objects. Citizen scientists can help analyze data from space telescopes. Online courses make advanced concepts accessible to anyone curious enough to learn. The quiet revolution is not happening in ivory towers, but in classrooms, living rooms, and backyard observatories around the world. As we approach the end of our contemplative journey through the possibilities of routine interstellar visitation, we arrive at perhaps the most profound question of all. What does this mean for humanity's understanding of our place in the universe? If our solar system is indeed regularly visited by objects from other stars, If we exist not in isolation but as part of a vast network of cosmic exchange, then we must fundamentally reconsider our role in the grand narrative of the cosmos. We are not isolated actors on a lonely stage, but participants in a drama that spans the galaxy, connected to distant stars through threads of matter, energy, and perhaps information that we're only beginning to perceive. The metaphor of cosmic flow becomes essential to understanding our situation. Just as Earth's oceans are connected by currents that transport heat, nutrients, and life around the globe, the galaxy appears to be connected by currents of interstellar objects flowing between star systems over millions and billions of years. These currents aren't uniform or predictable in the way ocean currents are, but they exist nonetheless, created by the gravitational interactions of stars, the explosive deaths of massive stars, the collisions of planets, and countless other cosmic events that set matter in motion across the vast spaces between stars. Within this cosmic flow, Earth occupies a particular position, not central, not special in any absolute sense, but unique in its specific combination of conditions and history. We orbit a stable, middle-aged star in a relatively quiet region of the galaxy, far from the intense radiation and gravitational chaos near the galactic centre, but not so far out that we're isolated from the flow of interstellar traffic. Our position has allowed life to develop and evolve over billions of years, possibly benefiting from materials and influences delivered by interstellar visitors, while avoiding catastrophic impacts that might have reset evolution entirely. Think of our solar system as a harbour in this cosmic ocean, a place where interstellar voyagers might pause, however briefly, before continuing their journeys. Some visitors, like Oumuamua, sweep through quickly, barely affected by our sun's gravity. Others might linger longer, captured into eccentric orbits that keep them in our neighbourhood for thousands or millions of years before they escape again. Still others might become permanent residents, indistinguishable from native objects unless we examine them closely enough to detect their foreign origins. The recognition of our place in this cosmic flow transforms how we think about resources and materials. Every atom heavier than hydrogen and helium was forged in the heart of a star or in the explosive death of a star. These atoms have been cycling through the galaxy for billions of years, incorporated into stars, planets, and interstellar objects, distributed and redistributed by cosmic processes. The carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, all have histories that extend far beyond our solar system. We are literally made of cosmic material that has travelled between stars, and we will eventually return that material to the cosmic flow. This perspective has profound implications for how we think about life and its distribution in the universe. If material regularly flows between star systems, then the building blocks of life, and perhaps life itself, might also flow between systems. The concept of panspermia, once considered highly speculative, becomes more plausible in light of routine interstellar visitation. Life might not arise independently on each habitable world, but might spread through the galaxy like seeds on the wind, taking root wherever conditions allow. Earth might not be an isolated garden, but part of a vast cosmic ecosystem where life flows between worlds over geological timescales. Our emerging understanding of our place in the cosmic flow also affects how we think about intelligence and consciousness. If we are part of a galaxy where matter and energy routinely flow between star systems, might information also flow? Could there be messages encoded in the trajectories of interstellar objects, in their composition, in their behaviour? Might some of the visitors passing through our solar system be not just random debris but deliberate messengers, carrying information from civilizations that understood the cosmic flow long before we did? The temporal dimension of our place in the cosmic flow is particularly humbling. Human civilization has existed for perhaps 10,000 years, a mere instant in cosmic terms. We've been capable of detecting interstellar objects for less than a century. We're like mayflies who live for a single day trying to understand the seasons. The cosmic flow operates on timescales that dwarf human experience, with patterns and cycles that might span millions or billions of years. We're glimpsing a single frame of a movie that has been playing since the galaxy formed and will continue long after our sun has died. Yet despite the brevity of our existence, we've developed the remarkable ability to perceive and understand the cosmic flow. Through science and technology, we've extended our senses far beyond what evolution provided. We can detect objects billions of light years away, analyze the composition of stellar atmospheres, and track the trajectories of interstellar visitors. We've developed mathematical frameworks that allow us to model processes spanning billions of years and distances spanning billions of light years. In a very real sense, we've become the cosmos becoming aware of itself, developing the ability to perceive its own processes and patterns. This self-awareness brings with it a kind of cosmic responsibility. If we understand that we're part of a cosmic flow, that our actions have consequences that extend beyond Earth and potentially beyond our solar system, how does that change our behaviour? The spacecraft we've sent into interstellar space will eventually become interstellar visitors to other star systems. The radio signals we've broadcast are expanding outward at the speed of light, potentially detectable by any civilizations within a growing sphere, now dozens of light years in radius. We're not just passive recipients of the cosmic flow, but active participants, already beginning to contribute our own objects and signals to the galactic exchange. The future of humanity must be understood in the context of this cosmic flow. If we survive and continue to develop technologically, we will inevitably become a spacefaring species, not necessarily because we choose to, but because it's the natural progression for any intelligence that develops in this cosmic context. The same processes that bring interstellar visitors to our solar system will eventually carry humans or our descendants to other star systems. We will transition from being a single planet species watching the cosmic flow to active navigators within it. This transition might happen sooner than we imagine. The detection of interstellar objects like Oumuamua has sparked serious discussion about missions to intercept and study such visitors. Several concepts have been proposed for spacecraft that could be rapidly launched when a new interstellar object is detected, catching up with it to study its composition and perhaps even return samples to Earth. Such missions would represent humanity's first direct interaction with material we know comes from another star system, our first conscious participation in the cosmic flow that has been shaping our solar system for billions of years. The psychological and philosophical implications of recognizing our place in the cosmic flow are profound. Many of humanity's existential anxieties stem from a sense of cosmic isolation, the fear that we're alone in an indifferent universe. But if we're part of a cosmic flow, if matter and energy and perhaps life and intelligence flow between star systems as naturally as rivers flow to the sea, then we're not alone even if we haven't yet detected other intelligences. We're part of a process larger than ourselves, connected to the rest of the galaxy through threads we're only beginning to see. This connectivity doesn't diminish the value or uniqueness of life on Earth. If anything, it enhances it. Each world touched by the cosmic flow develops its own unique expressions of the possibilities inherent in matter and energy. Earth's specific history, its particular combination of conditions, has produced forms of life and consciousness that might be unique in the galaxy. We contribute our own verse to the cosmic poem, our own solution to the challenge of existence. The cosmic flow ensures that these solutions, these experiments in being, don't remain isolated, but eventually contribute to the galaxy's collective exploration of what's possible. The concept of cosmic flow also provides a framework for thinking about potential contact with extraterrestrial intelligence. Rather than imagining contact as a singular dramatic event, alien ships landing on the White House lawn, we might think of it as a gradual recognition of participation in the same cosmic processes. We might discover that some of the interstellar objects passing through our solar system are artificial. We might detect patterns in the cosmic flow that suggest deliberate action rather than random motion. We might realize that we've been in contact all along, just without recognizing it. Our growing awareness of the cosmic flow is already changing how we approach the search for extraterrestrial intelligence. Rather than just listening for radio signals or looking for megastructures around distant stars, we're beginning to look for evidence of intelligence in the patterns of interstellar objects, in the distribution of unusual isotopes, in anomalies that might indicate technological activity. We're developing a more nuanced understanding of what contact might look like and how it might unfold. The educational implications of understanding our place in the cosmic flow are significant. Future generations need to be prepared for a universe where Earth is not isolated but connected, where interstellar exchange is routine, where humanity's future extends beyond our planet and even beyond our solar system. This requires not just scientific education, but philosophical and ethical preparation for our role as conscious participants in cosmic processes. We need to develop what might be called a cosmic ethics, principles for how we interact with the cosmic flow and potentially with other intelligences we might encounter within it. The technological developments sparked by our recognition of the cosmic flow are accelerating. New telescopes designed specifically to detect interstellar objects are being planned. Spacecraft concepts for intercepting such objects are being developed. Technologies for analyzing the composition of objects from a distance are improving rapidly. Each advancement increases our ability to read the messages carried by the cosmic flow, to understand our place within it, and to prepare for more active participation. The cultural evolution accompanying this understanding is equally important. Science fiction, which has long imagined humanity's future among the stars, is becoming less fiction and more serious speculation about possibilities. Artists are beginning to incorporate themes of cosmic connectivity into their work. Musicians are creating compositions inspired by the rhythms of orbital mechanics and the harmonies of gravitational interaction. Poets are finding new metaphors in the cosmic flow. Culture is beginning to reflect and explore what it means to be part of something so vast and ancient. The economic structures of human civilization will need to evolve to accommodate our participation in the cosmic flow. Resources that seem scarce on Earth might be abundant in space. Materials with exotic properties might be delivered by interstellar visitors, Energy might be harvested from sources we haven't yet imagined. The economy of the future might be based not on terrestrial resources, but on our ability to interact with and benefit from the cosmic flow. This isn't just about asteroid mining or space tourism, but about fundamentally reimagining human economy in a cosmic context. The political implications are equally transformative. National boundaries become less meaningful when we recognize that we're all inhabitants of the same small world in a vast cosmic flow. The challenges and opportunities presented by our cosmic situation require cooperation on a planetary scale. The detection of an obviously artificial interstellar visitor, for instance, would be a moment that transcends all national, cultural and religious divisions. It would be a species-level event requiring a species-level response. As we contemplate our place in the cosmic flow, we must also consider our responsibility to future generations. The decisions we make now about how we interact with space, how we develop technology, how we treat our planet, will affect humanity's ability to participate in the cosmic flow for thousands or millions of years to come. We're the generation that first became aware of the cosmic flow, and with that awareness comes the responsibility to act wisely, to prepare humanity for its cosmic future while protecting the precious world that has nurtured us. The spiritual and existential dimensions of our place in the cosmic flow cannot be ignored. Many of humanity's religious and philosophical traditions will need to evolve to accommodate the reality of cosmic connectivity. The idea that Earth is part of a vast flow of matter, energy, and possibly life and intelligence challenges some traditional beliefs while reinforcing others. We might find that ancient intuitions about our connection to the cosmos were more accurate than we realized, just expressed in mythological rather than scientific language. The search for meaning in human existence takes on new dimensions when we understand our place in the cosmic flow. We're not isolated beings struggling to find purpose in an indifferent universe, but participants in a cosmic process that has been unfolding for billions of years. Our search for meaning is part of the universe's search for self-understanding. Our curiosity about the cosmos is the cosmos being curious about itself. Our wonder at the beauty and complexity of existence is the universe experiencing awe at its own nature. As we near the end of our contemplation, it's worth reflecting on how far our understanding has come in just the past few years. The detection of Oumuamua in 2017 marked a turning point. The moment when interstellar visitation transformed from theoretical possibility to observed fact. In the years since, our understanding has evolved rapidly. We've detected more interstellar visitors, developed better models of their frequency and distribution, and begun to seriously consider the implications for our understanding of our cosmic situation. But we're still at the very beginning of this journey of understanding. The cosmic flow has been operating for billions of years before we became aware of it, and will continue for billions of years after we're gone. We're like children who have just discovered that the stream behind our house connects to a vast river system that eventually reaches the ocean. We can see the water flowing, we can begin to map where it goes, but the full extent of the system and all its connections remain to be discovered. The coming decades and centuries will likely bring revelations that dwarf our current understanding. We might discover that interstellar visitors are far more common than we currently estimate. We might detect unmistakably artificial objects passing through our solar system. We might find evidence that life has been flowing between star systems throughout the galaxy's history. we might realize that intelligence is not rare but common, that the cosmic flow carries not just matter and energy, but information and consciousness. Or we might discover that we're more alone than we thought, that life is extraordinarily rare, that intelligence is even rarer, that we're one of the few points of consciousness in a vast, mostly unconscious cosmos. Even this discovery would not diminish the importance of understanding our place in the cosmic flow. It would make our responsibility even greater, as possibly one of the few witnesses to the cosmic drama, one of the few entities capable of perceiving and appreciating the beauty and complexity of existence. The cosmic flow continues whether we're aware of it or not, but our awareness changes everything. It transforms us from passive objects moved by cosmic forces to conscious participants capable of understanding and eventually directing our movement within the flow. We're developing from cosmic infants, unaware of the forces shaping our existence, to cosmic adolescents, beginning to understand our situation and our potential. What will become as we mature into full cosmic consciousness is impossible to predict but thrilling to contemplate. As you drift towards sleep, carried by the gentle rhythm of these words like a boat on calm waters, remember that you are part of this cosmic flow. The atoms in your body have travelled between stars. The energy that powers your thoughts comes from our sun, which formed from the debris of earlier stars. You're not separate from the cosmos, but an expression of it, a way for the universe to perceive and understand itself. Every breath you take participates in the exchange of matter and energy that connects all things. Every thought you think adds to the universe's growing self-awareness. The interstellar visitors passing through our solar system are reminders of our connection to the greater galaxy. They're messengers from distant stars, carrying information about places we've never seen and might never visit. But they're also mirrors, reflecting back to us our own cosmic nature, reminding us that we too are travellers, riding our small planet through space, participants in the same cosmic flow that carries them. In recognizing our place in the cosmic flow, we find both humility and dignity. Humility in understanding how small and brief we are in the cosmic scale. Dignity in recognizing that despite our smallness and brevity, we've developed the ability to perceive and understand the cosmos. We're the universe becoming conscious of itself, developing the ability to appreciate its own beauty, to understand its own processes, to contemplate its own meaning. The question of routine interstellar visitation is really a question about connection versus isolation, about whether we're part of something larger or alone in the void. The evidence increasingly suggests that we're connected, that we're part of a cosmic flow that has been operating since the galaxy formed and will continue until the stars burn out. This connection doesn't guarantee that we'll meet other intelligences or that our future is assured, but it does mean that we're not alone in the deepest sense, that we're part of a process larger than ourselves, participants in a cosmic drama whose full scope we're only beginning to glimpse. As this documentary draws to a close, as you feel yourself drifting toward the peaceful realm of sleep, carry with you this thought. You are part of the cosmic flow. Every atom in your body, every spark of consciousness in your mind is connected to the vast processes that shape the galaxy. The interstellar visitors passing through our solar system are not strangers but fellow travellers, reminders of our participation in something magnificent and ancient and ongoing. The universe is not a cold, empty void punctuated by isolated islands of matter. It's a vast, interconnected web of matter and energy in constant motion, with streams and currents flowing between stars, carrying materials and perhaps life and intelligence throughout the galaxy. We're not outside observers of this cosmic flow, but participants within it, both shaped by it and beginning to shape it ourselves. Sleep now, knowing that you rest not in isolation but in connection. Not in a static universe, but in one alive with motion and exchange. The cosmic flow continues while you sleep, as it has for billions of years and will for billions more. Interstellar visitors continue their ancient journeys, some passing through our solar system right now. Invisible to our eyes, but real nonetheless. And you, in your small but significant way, are part of it all, a conscious point in the vast flow of cosmos becoming aware of itself. The stars above are not distant and unreachable, but neighbours in the cosmic community. The space between them is not empty, but filled with travellers, and Earth, our precious home, is not alone but connected, visited, and visiting in return. This is our place in the cosmic flow. Not as isolated observers, but as participants in a grand exchange that spans the galaxy and connects all things in ways we're only beginning to understand. Rest peacefully in this knowledge. You are home in the cosmos, part of its flow, connected to its vast processes. The universe that seems so vast and foreign is actually intimate and familiar, for you are made of it, and it experiences itself through you. In the cosmic flow there is no true separation, only temporary eddies of consciousness that emerge, perceive, wonder, and eventually return to the flow, carrying with them the experiences and insights of their brief but precious existence. The question of whether interstellar visitors are routine has led us to a deeper understanding. We ourselves are cosmic visitors, temporary arrangements of matter and energy that have come together to experience and understand the universe. In recognizing the routine nature of interstellar visitation, we recognize our own nature as part of the cosmic flow, connected to all things, isolated from nothing, participants in a drama whose beginning we can barely glimpse and whose end we cannot imagine. And so our contemplation comes full circle, returning to where we began but with deeper understanding. The cosmos is not a vast emptiness with isolated islands of activity, but a living system with constant exchange between its parts. Interstellar visitation is not extraordinary but routine, not impossible but inevitable, not rare but regular as the turning of galaxies and the birth and death of stars. And we, brief conscious beings on a small planet orbiting an ordinary star, are witnesses to this cosmic truth, participants in this cosmic flow, and perhaps, in our own small way, contributors to the universe's growing understanding of itself